60-degree angle sections, and we have compared their behavior with the existing 90-degree angle sections, and we have found out what are the merits and the demerits of using these 60-degree angle sections in communication towers. I will talk a little about on these communication towers, and then I will conclude my talk with a summary. And this is a overview, schematic view of a transmission tower. A transmission tower is nothing but a superstructure which is used to transmit electricity from the generating station. That is, generating station is hydroelectric, hydrothermal, or whatever the way of source the power is getting generated. The power has to be transmitted from the source to the consumer. It has to be traversed a long distance of kilometers. For that, we are using these skeletal structures. These transmission towers are statically indeterminate structures. The main components of a transmission towers are a leg member, bracing member, and the main function of a leg member is to resist the axial force. Whatever the axial force coming on the tower, the leg member has to resist. The bracing members, the main function of a bracing member is to resist the shear force. There are many types of bracing members like a K brace, X brace, and also we can see some of the in between leg and bracing members, we will use some redundant member. These redundant members are used to reduce the effective length of the leg members so that their compression capacity can be enhanced. And also we can see some 3 triangle-like portion at the top. They are called the cross arms. They will carry the conductors. They will support the conductors. And there are different types of circuits of transmission towers like a single circuit tower, multi-circuit tower, double circuit towers. And there is a peak. On the peak, you can see some two triangles. They are called as the ground wire peak. They are used to protect the tower from lightning. In case some lightning is happening, this ground wire peak will transmit that lightning power to the ground. That is the main function of the ground wire. And there are 3 types of loads will acting on a transmission tower. First one is the vertical load. The vertical load is due to the self weight of the tower and self weight of the conductor, and what are that will be simulated through the prototype testing. How much vertical load is coming on the tower, that will be simulated. That is due to the vertical load to conductor. And one of the main component of the wind load acting on a tower is the wind load. That there is a IS code called IS 875. There we have categorized our whole India into different wind zone maps. Suppose we have to design a transmission tower in a particular location, we have to select what is the wind zone, which wind zone we have to locate the tower. According to the wind zone, we have to design the tower. There are there is a particular code for a design of transmission towers. The main aspect of the design of a transmission tower is the tower is designed with a minimum factor of safety. Hence, the design of the tower has to be optimistic. Suppose we have to design a tower for a particular region, we will go for a very, very optimistic design of a tower. Hence, the weight of the tower will be very less. Hence, the tower has to be prototype tested for each and every tower before it is being implemented in the field. In India, we have a code called IS 802. That is the code we are using for the design of a transmission towers. IS 802 Part 1, Section 1, Part 1, Section 2. These 2 codes sections deals with what are the loads and how the towers are designed. These 2 codes will talk about this. And also we have to calculate what is the wind load on the conductor and the tower. These codes also will talk about how to calculate the wind load on the conductor. We have to for calculating the wind load on the conductor, we have to take the sag. What is the sag of the conductor? And based on that, we have to what is the temperature condition. Suppose if I want to install the tower in the hilly regions, I have to take a different additional load that is called ice load. That will also contribute to the self weight of the tower. And if the ice is deposited on the conductor, that will attract more wind load. That aspect has to be taken. This code will talk about this, how to take these different types of load acting on a tower. And the third component of load acting on a tower is the longitudinal load. Our code specifies that suppose if a tower is traversing a terrain, if under extreme wind condition, if one of the conductor breaks, then the tower will be subjected to some torsional load. Then the transmission tower has to withstand this type of broken conductor load, which is induced due to the conductor breakage. Hence, I will talk about what are the testing facilities we have, how we are simulating this broken conductor load in our testing station. We have one of the unique facility of this testing station in India. our unique facility is that we have hydraulic rams for the application of the load on the conductors. The unique when we compare the testing stations in all over the world, they have the winches for the application of the load, but we have hydraulic rams. The main advantage of this hydraulic ram is that we can apply the load in a very smooth way. That is, without any jerk, the loads can be applied. And if we notice any failure during the testing of these towers, we can stop the load at any point. That is one of the unique facility we have. Hence, the clients from all over the world will prefer to test their towers in our test bed. That is one of the unique facility we have. I will talk about what are the facilities we have in the next slide. This is a schematic view of a tower. I have talked about this is a tower extension. What is a tower body, and the types of cross arm and peak, and what are the types of load coming on the transmission tower. Next, this is a schematic view of our testing station. We have a test bed. There we will erect the tower. Depending upon the suppose a client is bringing the tower, first we will do some preliminary study. What is the force coming on the transmission tower? What is the foundation force? Accordingly, we will design what is the bottommost how to fix the tower. What is the base width of the tower? Accordingly, we will design the stub member, so that our main intention is to test the superstructure. We will design the foundation with maximum factor of safety. That is, we will there is a peculiar arrangement called a stub member. We will fix the bottommost leg member to this stub, and then we will fix the stub to the test pad. This test pad is constructed with the pre-stressed rock anchors. We will fix the stub with the maximum factor of safety up to 2, so that the foundation should not fail. Our intention is to test only the superstructure. And these are the 3 types of loading stations we have. First one is the vertical ram station. Here we have we are simulating the vertical load. What are the coming on the towers? That we are simulating through this vertical ram station. And the next one is called the transverse ram station, that is located at a hilltop of around 49 meters. There, through this ram station, we can simulate the wind loads. What are the wind loads are coming on the tower? That we can simulate through this. And we have one more ram station called a longitudinal ram station, that is located at a hilltop of 63 meters. Our testing station is located in a horseshoe shaped hillock, that is a naturally formed hillock, so that we are locating all these 3 ram stations in our test bed. And another criteria of testing the transmission tower is the major criteria is we have to monitor the deflections of the transmission towers. For that, we have to monitor continuously the deflection of the tower during testing. There are 2 types of deflections coming on the will be noticed. First one is the transverse deflection, and the other one is the longitudinal deflection. We will monitor the deflection through the total stations. We have 2 total stations in this transmission. We will in our test bed. We will continuously monitor the deflection of this tower during this testing, and we also have the facility of suppose before doing the prototype testing, we will do some preliminary analytical studies, and we will find out what are the critical members in the that may with the very less margin of safety that may fail during the testing. We will monitor that behavior of that particular member through the strain gauges. We have the data logger facility, and if we will monitor that particular member during strain. If any abnormal strain is happening, then we will stop the test. Then we will replace the member with a higher sections or higher grade of material. Then we will continue the testing. And this is the test pad. This is the top view of our test pad. Here we can test the transmission tower up to maximum width of 22.5 meter by 22.5 meter, and we have a rock anchor, pre-stressed rock anchors. These rock anchors can resist the uplift load of 550 tons, and we have tested the transmission towers up to maximum uplift force of 700 tons. That is the maximum uplift force we can test. And this is we have now the digital control system to monitor the loads applied on these towers. We have a 40-channel control system. I have shown here now. This is the typical view of transmission towers. At each point of tower, there will be 3 types of load has to be acting. That 3 loads will be monitored. What each point, that is cross arms or ground wire peak or body load, that has to be monitored. That will be monitored through this control system, digital control system. All the types of load, for suppose for a particular tower, depending upon the double circuit or single circuit or multi-circuit towers, the number of load points may vary. Suppose for a single circuit tower, the load points may be less. For a double circuit tower, the load point may be high. For multi-circuit tower, the load points will be very high. For that, we have up to 40 channel control system that we will monitor through this our control system. And we have one of the unique facilities that we have emergency stop. Once we press the emergency button, the loading will be stopped at that particular instant, and the loads will be automatically released. And one more unique facility of a testing station is a P delta effect. Suppose if we want the main criteria of testing a transmission tower is we should not apply load all in a sudden. First, we have to go for as per the IS code and as per the international standards. We have to first apply the load up to 50% of the load. Then we have to slowly proceed up to 75, 90, 95, and 100%. We have to take the deflection at all these stages of loading during testing. And this at any point of load, if we are noticing any distress, we can stop the load at any point using this emergency stop button. That is one of the unique facility we have. And this is the transverse ram station. These are the hydraulic rams which we are where we are connecting the load points to these hydraulic rams. From this hydraulic ram, the steel wire rope will be traversing through this transverse ram station. That is one tall structure is there, no? That is called a transverse ram station. That vertical ropes will be transversed through this vertical pulleys, and then it will be connected to the tower. The load cell will be fixed on the tower. Whatever the feedback we are giving to the tower, that whatever the loads will be sensed through this control system. The control system will give the drive to drive the actuators. Suppose we want to apply 10 kilonewton of load, the load cells will give the feedback to the control system that I have to apply the 10 kilonewton to this particular point. Then the control system will sense and it will give the drive current to the actuator, so that that will drive the actuators to pull the load. It will pull inside so that the required load is applied. Suppose I have around 10 load points on a particular tower, then our the P delta we are taking care into P delta effect. All the load points that once it reaches that all the loads that were desired load, until that the tower will deform, so that it will it will take care of the P delta effect. That is one of the unique facility we have in our testing station, in which suppose if we are pulling one load, but one load point we will apply one load and then we will stop. Then suppose if we are pulling a top point and then we are stopping that load, then we will come to the bottom point. In winch application, that will be a release of the load due to the application of the load. But in hydraulic, this our closed loop servo control system, it will take care of until all the desired load should be applied. That is, whatever suppose 10 kilonewtons has to be applied at all the 8 points, it will continuously give the feedback to the drive actuator, so that all the desired load is applied at all the loading points. Since the clients will prefer to test our testing towers in our test bed. And this is the longitudinal ram station. This is located at a hillock of 65 meter. Here up to 550 tons of load can be applied in this through this longitudinal ram station. This longitudinal ram station is to simulate the broken conductor load on the transmission towers. Broken conductor load means there will be different criteria when we go. The towers are be designed as per CBIP manual, Central Bureau of Irrigation Power. There they will specify that as per IS code also there are different criteria. Suppose if there is a single conductor broken at a time, two conductor broken at a time, we have to simulate all these criteria through this. These are called as security conditions. That conditions can be simulated through this longitudinal ram stations. And this is the vertical ram station. This is the top view. This is to apply the self weight of the self weight load on the transmission towers. And before each testing, we have to calibrate the load cells. We have different ranges of load cells ranging from 10 kilonewton up to 500 kN. We have the calibration facility in our testing station, and we will calibrate the load cells prior to each testing. And then we will, before these load cells are mounted on the tower, and that records that load cell feedback will be recorded in our control system. That data will be used while applying the load on the towers. That is one of our unique facility we have. Apart from this, I have already told, we have data acquisition facilities, and we have a tower crane for erecting the tower. Up to 5 tons it can lift. The lifting capacity is 5 tons, and the height of the tower crane is 72 meter high. We have tested up to 80 meter height transmission towers, and we have forklift capacity and tail-light stations for measuring the deflections. And we have a video camera for live webcasting, and we have workshop facility for fabrication facilities. Suppose if a tower member has to be replaced, that we have that we can immediately fabricate and we can fix on the tower during testing, so that the testing is not disrupted during the prototype testing. And we have some of the accelerometers to fetch the dynamic response of the small R&D towers we can do, and we have taken some vibration data on the full scale towers also. And then why we have to go for that? You may have some question that why analysis we are doing, then we are implementing in the field. Why we have to go for prototype testing? That question you may have, because we cannot simulate the bolted connections. That bolted connections is the bolted simulation connection is complicated. We have to simulate this bolted simulation is very complicated. Hence, we have to go for testing, and there will be some fabrication inaccuracies. And since we are using angle sections for transmission towers, there may be joint eccentricity. We cannot simulate these types of parameters in the FE modeling. Hence, we have to go for particularly necessarily go for a prototype testing of towers. And this is a statically indeterminate structure. There is a problem of structural instability will be happen. Hence, we have to necessarily go for a prototype testing of towers. And next, I will move on to a brief introduction of buckling. The term buckling was first coined by Euler in 18th century. He has proposed, as we all know that Euler buckling formula, he has proposed this buckling formula for short and intermediate columns. Then it was followed by Lagrange. He has proposed some improved version of this Euler buckling formula. Then in 19th century, Professor Salman, he has validated the Euler's theory for based on some experimental investigation. And as we all know that we are familiar with a particular term called slenderness ratio. That slenderness ratio was coined by Professor Lamella in 19th century. All these four are professors from Euler to Lamella. They have concentrated only on elastic buckling of columns. It was Professor Engesser and Karman in they have taken some keen interest on how that buckling behavior of inelastic columns, and they have proposed some formula and experimental investigation for to investigate the inelastic buckling of these angles and columns, angle sections. Then what is meant by buckling? Buckling is defined as a structural behavior. It is defined as whenever a structural element is deforms in a plane, which is whenever we are applying a load, the structural element is behaving in a plane which is different from the original plane of loading. Suppose if we are loading in a vertical direction, the structural element is deforms in a plane which is different from the plane of the loading. That is called as the buckling. That is the structure. The element structural element is deforming in a plane which is different from the plane of loading. That is described as the buckling, and it is purely a problem of it is occurring due to the unstable equilibrium between the loading and the internal response. Due to the unstable equilibrium of existing between the external loading and the internal response of the structure, the buckling is happening. It is purely unstable equilibrium. It is due to unstable equilibrium, the buckling is happening, and the buckling is controlled by the stress strain behavior of the material under consideration. For a tower, we are using some angle sections. These angle sections are monosymmetric sections, and here in these angle sections, they are the shear center will not coincide with the CG of the angle sections. What is meant by shear center means, suppose if we are applying the load through the shear center of a particular cross sections, it will not twist. But in case of angle sections, the distance there will be the shear center and the center of the angle section, center of gravity of the angle section will not coincide. Hence, these angle sections are susceptible for buckling, and this is buckling is a problem of. Hence, this buckling is considered as a problem of stability. There are different types of buckling, like flexural buckling, torsional buckling, flexural torsional buckling, local buckling, and distortional buckling. Flexural buckling is, suppose the structural element is deforms in a translation, only by translation, without any rotation, then it is called as flexural buckling. The flexural buckling is resisted by the flexural rigidity of the cross section. Suppose if the cross section is whenever subjected to a cross section subject to compression load, it is subjected to twisting, then it is called as a torsional buckling. The torsional buckling is resisted by the torsional rigidity, that is Gj, that is torsional modulus into torsional moment of inertia. In some cases, such as angle sections, if they are subjected to translation as well as rotation, then we call this as a flexural torsional buckling. I will talk more about this flexural torsional buckling in case of 60-degree angle sections towards the end of my lecture. And there are some types of buckling called plate buckling, local buckling. The local buckling will occur in a plate element. In angle sections, there are two flanges which are connected to form the angle sections. These two flanges will act as an individual plate element. Suppose if there are some occasions where this plate element will buckle before the angle section will reaches the problem of instability. That is, before the angle section buckling as a whole, the local plate buckling of these angle sections may occur. That I will talk in the next in due course. And there is one more type of buckling called a distortional buckling. That is intermediate between the local buckling and the member buckling. That will occur mainly in case of channel sections. And this is a basic buckling equation for elastic buckling equation for angles for an prismatic section. Let us consider a prismatic column of length L, that is uniform cross section. It is subjected to a concentrated load applied through the CG. While applying this, while the load is applied, there will be a lateral deformation of this prismatic section. The lateral deformation at a distance x, let us consider that as y. Based on these parameters, we are formulating a second order differential equation. This deformation is represented in terms of second order differential equation, that is I have given as EI d square y, that is a double second order differential equation. Sorry. This is represented as in terms of flexural rigidity and the external load and also the unit moment. Then I am assuming as the characteristic solution for this second order differential equation is y into c into n pi x by L. And after solving this differential equation, I am landing in this Euler buckling formula, that is pi square EI by L square. This pi square EI by L square is derived based on this fundamental origin, that is Euler buckling formula. One of the basic limitation of this Euler buckling formula is we has assumed that Young's modulus is constant. It is constant. It will not change once the buckling happens. And also one of the limitation is that that Young's modulus it is applicable only for simply supported beams. Suppose I'm sorry. Suppose we have in angle sections we have different types of boundary conditions, such as fixed or hinged and partially fixed. We have to take that into account. How to take into account those boundary conditions in this buckling formula? There suppose we want to generalize this buckling formula to take into account the different types of boundary conditions. Then we are coining a special word called effective length. That is called, in the denominator you can see L by R. There that L we are replacing by KL. That K will take care of this boundary condition effect. That is a fixed condition or a hinged end condition or a partial fixed conditions. That our code specifies how to take this effective length, that K factor, for different types of boundary conditions. IS 802 we can refer that if you are introducing this term K, then this Euler buckling formula will become a generalized formula, so that we can apply to the different types of angle sections with different types of boundary conditions. Next, this is applicable only for slender columns. Suppose there is one more term called inelastic buckling. Elastic buckling means this is only for applicable for elastic buckling. There is one more buckling called inelastic buckling. In inelastic buckling, I'm sorry. This theory of elastic buckling is only applicable where the compressive stress is uniformly distributed over the entire cross section, and the stress is well below the elastic limit. The elastic limit at the instant when the equilibrium becomes unstable. In case of short columns, suppose in slender columns, Euler buckling formula is okay. Suppose we go for a short end columns, there we have at the inception of buckling, there will be a term called a critical stress. There that column, there are different types of theory to take into account these types of the type of inelastic buckling. There are different types of theories are proposed. They are called double modulus theory, tangent modulus theory, and Shanley's theory of inelastic buckling. I will touch brief how about this theory in a few slides. First one is the double modulus theory. Here, suppose I am applying a compressive load on a flat section. There will be some tensile stress on one side, and there will be a compressive stress on the other side. the double modulus theory states that due to suppose the double modulus theory is formulated based on that the rate of stress strain increase due to buckling is directly related to the tangent modulus of the stress strain curve. That's rate of increase of stress strain curve is directly proportional to the tangent modulus. And one of the double modulus theory is, suppose if we want to, they have introduced a term called E bar. This E bar will be calculated based on the reduced modulus. This E bar is called effective modulus or reduced modulus. Whatever we have seen in Euler buckling is that the elastic modulus is constant through the inception of buckling, but this is a advanced version of that buckling formula. Here he has introduced a term called a reduced modulus. I'm sorry. This reduced modulus is computed based on the location of the neutral axis. As the section buckles, you can see here, as the second section buckles started buckling, the neutral axis will shift. Based on that shift of the neutral axis, we have to compute the reduced modulus. That is, they have coined two terms called I2 and I1. They are called the moment of inertia of the cross section, which is separated by the neutral axis. And this is the governing differential equation for how to compute the buckling as per the double modulus theory. Next, this is the double modulus theory equation representation. Here, once below there is one more term called proportional limit. Below the proportional limit, that is above the proportional limit, the buckling will be governed by the elastic buckling. Below the proportional limit, the buckling will be governed by inelastic buckling. And here, when we go for tangent double modulus theory for inelastic buckling, it depends upon two properties. That is, it depends upon the shape of the cross section and also the material property of the angle section. This double modulus theory. The critical stress will depend upon the cross sectional area and the material property of this cross section. And one more theory has been coined that is called the tangent modulus theory. This tangent modulus theory states that beyond the elastic limit at certain critical stress, the state of equilibrium configuration, the deformation is controlled by the tangent modulus. That is, beyond the elastic limit, the deformation of the angle section is controlled by the tangent modulus. That is, as we have shown from in this slide, the tangent modulus, the stress strain curve, the deformation of the angle section beyond the elastic limit. Once the section crosses the elastic limit, the buckling is governed by the tangent modulus. This one. This tangent modulus, they have coined the term called E tau. This is called the tangent modulus. This is the tangent modulus is the ratio of elastic ET by E. This how to compute that ET I will show in due course. And this tangent modulus theory states that in the double modulus theory states that the buckling is governed by shape of the cross section and the material properties. But the tangent modulus theory states that tangent modulus buckling load PT is governed purely by the shape of the not affected by the cross section. It depends only on the elastic plastic properties of the material. And this is a comparison of a double modulus theory and tangent modulus theory. It states that whenever we are computing the buckling load in the inelastic buckling range, in the below the slenderness ratio of 70, the buckling load computed by tangent modulus theory will always be less than the double modulus theory. It states this is for a particular cross section. When we compute the buckling load as per tangent modulus theory and double modulus theory, the tangent modulus theory buckling load will always be less than the double modulus theory in the inelastic range of buckling below the slenderness ratio of 80. Next, we will go for a Shanley's theory of inelastic buckling. The Shanley's theory is represented here. It states that the buckling, the column will, he states that the Shanley's theory states that the column will tend to buckle once it crosses the tangent modulus buckling load until it reaches the unstable equilibrium. That is, it will be subjected to the rate of tensile load is governed by the cross-sectional deformation behavior, while the compression load is governed by the equilibrium between the externally applied load and the internal stress of the structure. The Shanley's theory is schematically shown as two hinge section, so that is which are infinitely rigid with the elastoplastic hinge at the bottom. It states that this hinge will continue to deform once it crosses the tangent modulus buckling load until it reaches the double modulus load. That is, it is in between the tangent modulus and the double modulus theory. It states that the column will continue to deform in between these two buckling loads. That is stated by this Shanley's theory of inelastic buckling. And here is this is he has Professor Shanley. He has validated his theory on a buckling load on a steel cross section, that is angle cross section, that is a cross sectional area with a circular cross section, and he found that whatever he has proposed is that cross section has continued to deform after crossing the tangent modulus buckling load until it reaches the double modulus theory buckling load. Next, we see these are, so far we have seen what are the theories of the buckling load, such as tangent modulus theory, double modulus theory, tangent modulus theory, and Shanley's theory of inelastic buckling. Next, we will see how to compute the buckling curve for a particular. Suppose we are given a cross section, how to compute the buckling curve. What are the parameters we require? We will see. Those parameters are, first we will need the modulus of elasticity of the material, and what is the tangent modulus, and what is the yield stress and its proportional limit. These proportional limit for the will vary depending upon the grades of the grade of the steel. Suppose if we are going for a mild steel, that proportional limit is we will assume as 70 to 80% of the yield stress. Beyond the proportional limit, that is, suppose beyond the between the elastic limit and the proportional limit, the buckling is governed by inelastic buckling. Beyond the proportional limit, the buckling is governed by elastic buckling. We should have these parameters to formulate the buckling curve. And beyond the elastic limit, that is beyond the proportional limit, the buckling is governed by Young's buckling formula, that is nothing but OS buckling. Below the proportional limit, the buckling is governed by below the proportional limit and the yield stress, the buckling is governed by Young's buckling formula. That is similar Euler's buckling formula. Only thing is that Young's modulus is replaced by the elastic E tau, that is tangent modulus. We have to compute the tangent modulus. This tangent modulus has to be computed based on the stress strain curve. That is, we will conduct some coupon test for a particular cross section. From the stress strain curve of this particular cross section, suppose if you are taking an angle section, if you are conducting a coupon stress, we will get some stress strain curve. From the stress strain curve, we have to define the proportional limit, and from the proportional limit, we have to compute this elastic tangent modulus. For different types of L by R, what is the different? For a different L by R, this elastic tangent modulus will vary. From that, we have to compute this elastic tangent modulus. And this is the relation between the, I have shown, no, I have told previously, this is the formula to compute how to compute the E tau, that elastic tangent modulus. It depends upon these parameters. That is, what is the yield stress, what is the critical stress at the particular slenderness ratio. That is, if I take a slenderness ratio of 10, what is the critical buckling load for that particular slenderness ratio, and what is the proportional limit we have assumed. We have to have these parameters to compute the what is the stress at this elastic modulus for this particular yield, this is particular stress in the inelastic buckling. And this is a quadratic variation between the elastic modulus and the tangent modulus for this inelastic range of buckling. And this is a quadratic variation. When we see a buckling curve, first I will see the next slide. This is a buckling curve. You can see first between up to slenderness in that is lambda p. I have shown that lambda p is the proportional limit. Between the proportional limit and sigma y, that is critical stress, I have shown as a Young's buckling formula, that is pi square E tau by L square, that we can compute using this formula. That is, I have given this formula, no, the quadratic variation. That variation is governed by this quadratic variation of buckling. And the variation of buckling in the elastic range, that is beyond the proportional limit, I have shown lambda p. Beyond lambda p, the buckling is governed by this formula, that is pi square. As usual, we know that pi square E by L by RVP, that is minimum radius of variation. How to compute the proportional limit for a particular yield stress is given by this formula. We can compute this for any cross section using these parameters. We can compute the buckling curve. Next, we will see how what is the influence of the shear on the shear force on the buckling load. And this is a typical 90-degree angle cross section. The shear center will be located at the intersection of the flanges. The center of gravity will be located far away from the shear center, as I have already told. And US is the distance between the shear center and the center of gravity. T is the thickness of the angle section, and UU is the major axis of buckling, and VV is the minor axis of buckling. And here is the theoretical formulation of how to take into account the shear force on the buckling. This is the formula to compute what is the influence of shear on the buckling load. This is available in theory of elastic stability by Blake. I have taken from that. And this is the buckling load. This is flexural buckling load about a major and minor axis. Considering the influence of shear, we can compute using this formula. And what is the buckling load due to torsion? We can compute using this formula. And this is the torsion flexural buckling. One more term I have already told. This is how to compute the torsion flexural buckling formula for the angle sections. In torsion flexural buckling, there is one more term called warping constant. We have to compute the warping constant using this formula. That is, B is the width of the angle section, T is the thickness of the angle sections. And I have given this. These formulas are available in that the textbook. We can use this formula for to compute the warping constant. And here I have conducted a parametric study on what is the influence of shear on the buckling load. Here we can see that the shear load is predominant in the inelastic range of buckling. Once the buckling, the transition of buckling happens from inelastic to elastic buckling, the influence of shear force on the buckling load is 0. That we can see. The curve flattens. That is, it has a major influence in the inelastic range of buckling. The shear force has a major influence in the inelastic range of buckling than the elastic range of buckling. We have formulated a formula how to distinguish the limit for proportional limit for yield stress, considering this influence of shear on the buckling load. What is the proportional limit for the slenderness ratio, considering the influence of the shear on the buckling load? This is the formula. The effective length governing the transition from inelastic buckling to elastic buckling can be computed using this formula, whatever we have proposed. We have proposed considering that once the shear load factor reaches the value of 0.8, the flat plateau is observed. By substituting these values in the above these equations, we have arrived at this limiting value for the slenderness ratio. Next, we have these are some interaction studies on flexural and local buckling. And here, this is a typical angle section. And as the angle section buckles, there will be a bifurcation of the flanges of the angle section. And this is the amplitude of the eigenvector, that is the amplitude of the buckling. This is in plane buckling. And this buckling is governed by this Euler buckling formula. And one more term is called plate buckling. This plate buckling is, as I have already told, the angle section is composed of two flanges. Each of the flanges may act as a plate element. And this is the how to compute the plate buckling of this angle flange section is computed using this, as we already familiar with this plate buckling formula. This is available in theory of elastic stability by Timoshenko. We can refer that formula. That is a critical buckling stress for plate buckling. In some instances, there are occasions where these flanges, this plate may buckle prior to the column buckling load. There are some instances are there. How to tackle those that scenarios, I will talk in this next slide. That is the interaction of flexural and local buckling. This local buckling may happen due to the local buckling of the plate elements. Hence, that Euler buckling is equated to the plate buckling equation. That is supposed to take into account this local buckling due to the plate element, buckling of the local plate element. The Euler buckling formula is equated to the plate buckling equation. Then we land in a particular term called a B/T ratio. That B/T ratio is the limiting ratio for the angle sections. The code has recommended that when we are designing an angle section, it should be within this B/T limit. Suppose if we are taking one angle section, it should satisfy the B/T limit, so that that plate buckling will not happen when we are designing the angle section within the BBT limit. Once we cross that BBT limit, then the plate buckling may happen before the angle section buckling started to buckling as a whole. That criteria has to be taken. That has been formulated. That BBT ratio is, this is the basis how they have computed the BBT ratio for the angle section. That is, first they are equating the Euler buckling formula to the plate buckling formula. Then they are computing, they are landing in this equation. That is, at the when the stress is below the proportional limit, then we can assume tau was 1, and then we can compute the BBT limit square. And then since we are assuming that plate element as a simply supported on three edges, and it is free on the fourth edge. Hence, we can assume the plate buckling coefficient as 0.425, and then we are substituting this equation, and we are landing in this equation. And this is the critical stress. How to compute the buckling equation in the tangent using tangent modulus theory. This is a critical stress, taking into account the local plate buckling. And this is the for a particular for a 355 MPa grade steel. And here for the as the L by R ratio varies, for different BBT ratio, how to compute this? This is T is nothing but tau. Tau is equal to ET by F. You can see that elastic tangent modulus will vary from 1 to 0. That how you can see from the nonlinear range, it will have a major effect. And then for different L by R, how the elastic tangent modulus is varying. This is for a topic for a particular grade of steel, 355 MPa. And this is a buckling curve for a leg member where both the flanges are connected. And we can see a linear variation in the elastic buckling and non-linear variation in the inelastic buckling. And here, and in our code, we can see that limiting BBT ratio is 12. Here, that BBT ratio is computed based on this this experimental investigation. For that they have assumed as that yield as 96% of yield stress. In the inelastic buckling, the proportional limit is considered as 96% of yield stress. That is intersecting at L by R of 42. That is limiting L by R. For that limiting L by R 42, the corresponding BBT ratio is 11.32. That is for the code BBT ratio mentioned in our code is based on this interference. That is 12. Our code IS 802 mentioned the BBT ratio as 12. That is figured out based on this experimental and theoretical investigation that we have conducted at our SERC. Although this is the interaction, what I have told that this is a limiting critical stress for plate buckling failure. To compute the, suppose if we want to compute the buckling load due to local plate buckling, this is a critical stress is computed using this formula. And suppose in some cases there are some occasions where the local plate buckling may occur due to stress concentration in the bolt holes. Apart from plate buckling, there will be a localized stress concentration near the bolt hole. Then the buckling may happen due to the stress concentration near the bolt holes. Suppose if we are in case of a leg member, we will connect both the flanges. In case of bracing member, only one flanges will be connected. Those angle sections are susceptible to stress concentration near the bolt holes. There, the buckling of angle section may happen due to the stress concentration of this near the bolt holes of these bracing members. Some case studies we have conducted that I will show. This is how to compute the BBT ratio of this compression member and for flexural member. For compression member, we have to take into account the entire width of the angle section. For a flexural member, from the fillet radius to the edge of the angle, we have to consider. And as I have told that this is nothing but as per IS 802, the BBT ratio is 12. That BBT ratio for a mild steel is for 355 MPa steel is 12. And the different codes, there are British code, American code, and Canadian codes. They have different criteria to compute the BBT ratio for the angle sections. And this is a case study on a plate buckling study on a K-brace panel. This is a K-brace panel. The panel was designed so that the target member of failure is the bracing member. Here we want to study the stress concentration, the failure due to stress concentration apart from the plate buckling. The two types of panel have been fabricated. First one panel with the hip bracing member. Hip bracing member is nothing but there is a member connecting to the leg member to the bracing member. That is in between these two, the bracing member, there will be a two bracing member will be connected through one more member that is called a hip bracing member that view I didn't show, and one more member without any hip bracing, one more bracing member without any hip bracing, and that panel was subjected to lateral load at top, and that failure we can see here. Here you can see that panel member has failed due to the stress concentration near the bolt hole. Here, apart from plate buckling, due to the stress concentration near the bolt hole, that angle member has buckled. Here, what is the remedy to overcome this stress concentration buckling? That is, this type of buckling is, we cannot, if we are increasing the reason is that the column has reached the buckling load since due to the stress concentration near the broken, due to the stress concentration near the bolt holes. It was found that if we increase the slenderness ratio, it will not improve the buckling formula. If we increase the slenderness ratio, that it will not have any effect in increasing the buckling load unless until we have to increase the thickness of the angle sections. That is the only remedy to take care of this, to prevent the buckling due to stress concentration in these angle sections. And as per the AAC code, the buckling load estimated as per AAC is overestimate the strength of the angle section because they are conducted at the element level on the angle section. That the behavior is completely different in the structural level. That strength is always overestimated in the code. That member behavior is completely different in the component level than at the structural level. Our IS code is similar to IS 802, similar to AEC 52, except the conversion of the units. Here, if you are, this is a component level testing on a bracing member, and this is a structural level testing. The member behavior is completely different in these two scenarios. Here, we are completely simulating the end conditions, but in structural, it is completely different. Hence, the buckling strength estimation from the component level and structural level is always different. And we have in TTRS and tower testing and resuscitation, we have tested towers for many clients from East, Middle East, and Far East countries, and there are some premature failures we have noticed in this tower. About 23 to 25% of premature failure existing in the towers, and one of the, as per the codal regulations, the computation of BBT width to thickness ratio, we are computing as from the root fillet radius to the edge of the fillet. It has to be computed from the nominal width of the entire width of the angle section has to be taken in computing the BBT with BBT ratio of the angle section. And this is the what is the influence of BBT ratio? Here I can see, we can see that in the inelastic buckling, the stress is reduced by 20% of yield stress when we consider the BBT ratio. Without, suppose if we are designing the angle section without the BBT ratio, then we will be overestimating the strength. Hence, we have to consider the BBT ratio in the design of the angle section. That is a considerable reduction of stress in the inelastic buckling edge. When we consider the slenderness ratio of 40, there is a drastic reduction in the yield stress. If we didn't consider the BBT ratio, then we will be overestimating the strength. Then we may experience the premature failure of these angle sections during testing. And these are some of the failure of the cross arms. That is due to local plate buckling. This failure has occurred. This is because of the stress concentration in the plate buckling in the angle sections. Then this type of failure can be overcome by introducing a redundant member. By introducing the redundant member will not overcome this type of failure. Only remedy is we have to increase the thickness of the angle sections. And this is another type of failure of a K-braced panel. Here we have seen that the BBT ratio of this angle section is 14, whatever they have taken. That limiting ratio is BBT ratio is 12, but because of this excess BBT ratio, it has introduced a greater eccentricity, abnormal eccentricity in the joints. Due to this eccentricity, it has induced some bending stress in the joint region, and because of that excessive bending stress, this failure has happened. And nowadays, we are using some high tensile strength steel for angles leg members in transmission tower. Here, the failure will not be gradual. When we go for high strength steel, the failure will be sudden. That may trigger the collapse of the tower, where the local buckling here they didn't take into account the local plate buckling in the interaction in this formulation, the design. Hence, the tower has collapsed. Next, we will go for the buckling of alternate angle sections. Here, I will talk about there are these are the 90-degree angle sections we are using for conventional lattice towers. We are one more type of angle section called schifflerized angle sections and 60-degree angle sections. Why we go for this schifflerized and 60-degree angle section is that in case of communication tower, triangular communication tower, when we go for 90-degree angle sections, then we have to go for a bent up gusset plate. That is not advisable when we go for communication towers, because there is a local instability problem may occur. Hence, we go for either schifflerized angle sections or 60-degree angle sections. And these are the geometric properties of a schifflerized angle section. Schifflerized angle section is nothing but the normal 90-degree angle section is bent inwards at certain distance far away, that is particular distance to 60 degree, so that it can be used for the construction of triangular communication towers. And we did some R&D on this. For this 60-degree angle section, the buckling is governed by equivalent radius of gyration. That is equivalent radius of gyration. This equation, this has to be computed using the ASCE 1015 code. This formula is available in that American code ASCE 1015. This we have to take into account while computing the torsional flexural buckling of this 60-degree angle section. As I have told that we will see more in deep in the next few slides about this torsional flexural buckling. Here we did some R&D on the 60-degree angle sections. This is a cold form 60-degree angle sections. These 60-degree angle sections are press braked by 260 degree and with the cold form plates. And we have derived some formulas based on the ASI standards. And here we have idealized the 60-degree angle section as a flat and curved element. And based on this, we have derived these geometric properties of these 60-degree angle sections. And here, this is a parametric study. What for a 60-degree angle section, there is a main parameter called root radius. That wherever which we are bending the angle section, there is a particular parameter called root radius. How the influence of what is the influence of root radius on the torsional flexural buckling? We have conducted some studies. We have noticed that as the root mean radius is decreasing, the governing effective length governing the torsional flexural buckling length also decreases. As we increase the root radius, the governing effective length governing the torsional flexural buckling also increases. And this is the buckling curve we have formulated for the 60-degree angle sections. Here we can see that in the inelastic buckling range, we have introduced one more term called RTF, that is called equivalent radius of gyration. And this is as I have already told, these are our formulated equation for the inelastic buckling and the Euler buckling. And this is our proposed buckling curve for the 60-degree angle sections. And we have conducted some experimental investigation on the 60-degree angle sections. Here we have instrumented with the dial. We have selected the specimen so that the specimens are susceptible only to torsional flexural buckling. And we have tested this in a UTM, that is advanced UTM machine. And we have measured the lateral deformation and also the axial deformation of the specimen. And we have simulated the hinged and boundary condition through this ball setup arrangement. And these are the failure modes. And these are the sustained behavior and the axial deformation behavior of this angle section. Here we can, from the load versus lateral deformation, we can see that there was a positive and negative trend. It means that both the flanges are opening out along with the translation, indicating that the section has failed in torsional flexural buckling. And this is our proposed curve for the 60-degree angle section and our comparison with the AEC code and our proposed formula. And we can see that there was a larger deviation was existing in the shorter effective length. This is because of the effect that we didn't take into account the local plate buckling effect in the formulation. We are fine-tuning that formula to take into account that plate buckling effect in this on our formulations. And we have validated our formulation, that buckling curve formulation on a tower, on a triangular tower fabricated with the 60-degree angle sections. These are the design parameters we have achieved, we have assumed for our study. And this is the we have modeled the tower in any Nastran software, and we have modeled all the angle sections using a 4-noded flexural element, and we have given the stress strain curve, whatever the coupon test we have conducted, that stress strain curve we have given as an input for modeling this to simulate this non-linear stress strain parameter, and we have completed the model the entire tower using the 4-noded flexural elements, and we have applied the load at 3 points at 5.5 meter and 4.5 meter and 3 meter, and this is the during experimental investigation. The tower, the whatever we have, this is a load versus load deformation behavior. Here we can see that a larger deviation exists between the experiment and the FEA. This is because we have to take into account the bolted connection effect. This is because in FE we are assuming only a pin joint assumption for the bolted connections. To further fine tune, we have to take into account that bolted connection effects also in this modeling. Once we take into account, then we may have a closer match between the experiment and FEA. Apart from this is an analytical comparison of a communication tower made of 90-degree angle section, schifflerized angle section, and 60-degree angle sections. These are the design parameters we have assumed. We have taken a 24-meter high triangular communication towers, and these are the design parameters we have used. And this is the FE modeling of this tower of made of a 90-degree angle section. And this is the FE model of the tower made where the leg members are made of 60-degree angle sections. And this is the FE model of the tower where 90-degree angle sections. And this is a deflection comparison of all these 3 towers. Here we can see that the tower with the 90-degree angle section has deflected more in comparison to the tower made of 60-degree and schifflerized angle sections. This is because of out of plane buckling. The excess deformation has noticed around 70% of load. This is due to the excessive deformation of the gusset plate in the joints. In summary, we can see that the torsional flexural buckling of leg member is observed in the numerical analysis similar to experimental investigation. And for triangular communication tower, the 90-degree angle section with bent up gusset plate has deformed more. The deflection was found to be 40% higher compared to the other 2 towers. And in the triangular tower using the schifflerized and 60-degree angle sections, there is a reduction in weight of around 20% compared to the triangular tower made of 90-degree angle sections. These are the references I have made. Thank you very much. If you have any questions, I am happy to answer.
Thank you, sir. Thank you very much.
Thank you.
Things are like you have given a very brief explanations. In a that is a fundamental explanation has been given, sir.
Yes, sir.
And the thing is that you have mentioned that you were analyzing the schifflerized angle and 60-degree and 90-degree.
Yes.
Yes, sir.
Yes, sir.
Normally, in recent erection of towers,
okay,
what is the structural, that is what kind of angle section they are using, sir? Whether you have recommended 60-degree or schifflerized angle based upon your research, or as a traditional way, or as a
no. So far in our country, we are using only as of now we are using only 90-degree angle sections. Okay. Now we are recommending to the Bureau of Indian Standards so that why can't we use these 60-degree and schifflerized angle sections for triangular communication towers in our country? That recommendations we are giving based on our R&D results.
Okay, sir. Okay. Yeah. Okay, sir. Okay. So apart from that,
yeah.
Regarding the involvement of what to say, the thermal stresses, because we are accounting the loads, that is a wind load or something like that. Yeah. How about the other loads that we have to account into it for the analysis, sir? Because steel members are subjected to thermal stresses also.
Correct. Thermal stresses, no, that thermal stresses parameters in the conductors where they have given how in transmission towers how to account for the thermal stresses. That parameters are given in the sag tension calculation of the conductors. Okay. Suppose if a high temperature is there, what will be the sag and what will be the influence of those high temperature effect on the tension load on the tower, and also if extremely low temperature, if it is ice accretion on the conductors. That parameters are given in the CBIP manual. How to take into account these temperature effects in the load calculation.
Okay, sir. Okay. So normally in the tower testing research stations, you will be including the parameters like apart from thermal stresses, or only the normal conventional load parameters you will be accounting it.
No. That will be converted into whatever the temperature effects are. Including the temperature effects, they will calculate the loads. That loads will be simulate. We will not simulate the temperature stresses. Whatever the temperature stresses have been taken into account while calculating the loads on the towers. That loads we will simulate here.
Okay. Sir, how about the composite member?
Yeah. We are doing experiments on these composite angle sections also. We have conducted some. We have used some GFRP angle sections for this for communication towers, and we did some results. And we have used these composite angle sections for strengthening of towers, existing towers. We have got some good results in conducting these experiments. Soon we will publish these results.
Okay, sir. Okay.
Yes.
Thank you, sir. Thank you very much, sir.
Thank you, sir. Thank you.
And I thank our on behalf of our department. It was our pleasure to invite you, sir. Despite your busy schedule, you have given a very fundamental explanations, and we are hoping for the next session also. Thank you,
sir. Thank you, sir. Thank you, sir. Thank you very much. I thank Dr. Sailo, HOD department, head of the department, Dr. Nirban Laskar, and Sri Vignesh Kumaran for giving me this wonderful opportunity to share my experiences with the students and our students of Mizoram University and students and faculty of Mizoram University. Thank you very much, sir. Thank you.
Thank you, sir. Thank you.
Sir, next session shall we start another 10 minutes?
Yes, sir. Yes, sir. We can start within 10 minutes, sir.
Okay.
Yeah, sure, sir. So I request the participants to be online. Within 10 minutes, the next session will be commenced.
Good morning, Mr. Vignesh Kumar.
So good morning, sir. Very good morning, sir.
Am I audible?
Yes, sir. You are audible, sir, and I think your video is not our. We couldn't see your video.
Okay, I am ready. You say okay, we'll start.
Sure, sir. Sure, sir. Uh,
Hello.
so morning, sir.
Good morning. Good morning to Sri Vignesh Kumar and HOD and other faculty members, my dear students, research scholars and PhD research scholars and MS, MTech, all students. Good morning to all of you. I am Prasad Rao, working in tower testing research station for the past 25 years. And I have witnessed around 350 tower testings and communication towers and other accessories like insulators, post insulators, other steel tower-like structures. And we have designed, we are the first laboratory to design a communication tower in India for Department of Telecommunication, 100-meter tower, when it was introduced in 1993, around 90s. And in every village, there is a 15-meter tower having an antenna, small antenna, that was first designed by SCRC. And it has so many numbers they have put in each and every village. And then slowly, so far in India, we don't have a code for communication tower. And we have developed a code after 15, 20 years. Though our communication tower network has started in 93 to 95, still it is improving. Now we have around 4.5 lakh towers all over the India, constituting of self-supporting guide towers, monopoles, so many rooftop towers, other things. And today my lecture will be on transmission line towers and small portion on communication towers. It will be for all UG students, PG students, and research scholars. I will give some introduction.
Yes, sir. Could you please give us 2 minutes? Sir? That is, we will be introducing you, and we will start the session directly after the introduction. Sir.
If time permits, I will show elaborately. Otherwise, we will restrict it up to that.
Yes, sir. Yes,
sir. Shall I start?
Sure, sir. Sure, sir. You can start,
okay,
sir.
Okay. Okay. See, what is transmission? Okay. 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 Now I'm starting. Once again, good morning to all of you. Okay. Now we'll see analysis, design, and failure investigation of transmission line towers. See, these are the governing bodies. Suppose if we have to put a transmission line tower in India, we have to get approvals from Central Electricity Authority. And guidelines, we have Central Board of Irrigation and Power that gives some guidelines, and National Electrical Safety Code. Then all over the world, we have Institute of Electrical and Electronic Engineers, IEEE. Then in India, for transmission line tower, is having a separate code. It is not governed by IS 800 or IS 875. Some wind loads are taken from IS 875 and it is converted, I will tell while going inside. we have two parts, IS 802 2015, that gives about loads and other things. IS 802 part 1 section 2, it talks about design of transmission line towers, members. Why a transmission line tower is required? See, we are producing power in different places, and that has to be transported to the utility center. Suppose, for example, we are producing a power in somewhere in the northeast, and hydroelectric power. It may be hydroelectric power, and thermal power, or solar power, or wind power, or wave power. That is generated in direct current as a 2.3 to 30 kilovolt, and that has to be transported depending upon the volume of the power that is generated in megawatts. Depending on the megawatts generated, we need to transport that in different voltage classes. Suppose power itself is less, 10 megawatt and other things, then we can go for 132 to 220 kV towers. If you transport the power in a higher voltage, the losses will be very less. So as the power volume increases, we have to increase the voltage transmission. So we can go up to 765 in India. We are trying for 1000 kV also transmission. As the voltage class increases, your conductor diameter will increase. The capacity of the conductor has to be increased. As the conductor capacity increases, then the clearances between one conductor to other conductor will increase, and your overall tower height will increase. As the tower height increases, your loads will increase, your moment at the base will increase, your base width will increase. So many things, parameters are increasing. So here we call it as a conductor is the productive cost. The ultimate aim is to transport the power from one generation station to utility center. Whereas these structures, transmission line towers, they are only a supporting structures. That is called non-productive cost. So productive cost is conductor. Conductor diameter you cannot reduce depending on the voltage, it is fixed. And material cost, everything is fixed. Whereas transmission line towers are required in huge numbers, and it's a repetitive structure where we require an optimization. At the same time, it should be reliable also. And mostly it is transmitted as an alternative current. And some lines where it's hundreds of kilometers straight, that has to be transported. Then we can go for high voltage direct current. But the equipment required in direct current transmission is very costly. That's why people is coming to the Delhi. We have to distribute from there. No? Then we have to go for the step down transformer, and reduce the voltage to 11 kV, and then distribute to industry or residential areas and other workshops or other industries. So if you go for a higher voltage, your losses will be less, transmission losses will be less, and it will increase the efficiency. So this is a typical transmission line system. You can see as my left side in the top is single circuit. One circuit consists of 3 conductors. If you see here, the conductor is supported by somewhat V-shaped insulator string. So we have V configuration. And the right side, if you see, it is a double circuit transmission line system where we have left side 3 conductors, right side 3 conductors. We call this as double circuit. Similarly, we can go for multi-circuit also. Each side 6 conductors. That is called multi-circuit tower. And if you see in the bottommost transmission right of way, as the transmission line is used, there should not be any vegetation, there should not be any trees. So this much land it is occupying this much land. So instead of putting 220 kV 2 towers parallel, we can go for a 760 kV line to evacuate the power that is being generated in the generation station to save the land cost. And if you see the typical transmission tower will have conductors, then conductor is connected to the cross arms. We call that is a cross arms cantilever portion. From there, it is connected to the conductor by an insulator. Insulator is the via media which separates the tower steel tower from the conductor, so that electrical outages, electrical short circuits will not come. So this insulator length will depend on the voltage that is being transmitted in the conductor. So it varies from 1.5 to 3 meters also. So here you can see all II. We call this as III. Insulator is vertical. There is no V. So III configuration. And we call this a suspension tower because the conductor is suspended from one support to other support. Whereas if you see the middle figure, here we have conductor is in tension. See, that means conductor is right away connected to the tower in the horizontal position. So this is after some certain number of suspension towers, we require a minimum tension and we require an anchoring tower. Suspension towers are very light. This is maximum optimized. And once it fails, the failure should not propagate to 10 to 20 towers, 30 towers like that. And each tower is spaced around 300 to 400 meters. So for that, we require an anchoring tower, what we call an anti-cascading tower and tension tower. That will be stronger when compared to this suspension tower. That will stop the failure propagation beyond that tower. So for every 10 towers, there will be one anti-cascading tower, we call tension tower. Then we have terminal tower. Once you come to the utility center, there we have to terminate the line. We have line on one side only, conductor, other side, it will be going to the substation. There it will be, voltage will be reduced and it will be distributed to the distributors. So the main function of the transmission line tower is to keep the air gap between the conductors in between, and then to keep the conductor at a certain level, certain height from in the field. The typical self-supporting transmission line tower and their parts I am showing you. And if you see here, 3 cross arms we have, and 3 cross arms. Then we have 2 ground wires. The function of ground wire is to protect the conductors from lightning strokes. This number of ground wires depends on the number of isosironic level in that area. That means number of thunderstorms per year. Based on that, this will be decided, and also the shielding effect. I will come back to that. So how much the shielding it can give. Up to 20 degree it can give the shielding. So that should be protected. The conductor should be protected. So it depends on that criteria, number of ground wires. Then if you come to the structural level, we have a configuration. It's basically it's a cantilever structure anchored to the foundation. If you see here, this is called a panel. Since the shape is like K shape, we call it a K bracing panel. K brace panel, you can see in the right side. And then next is the X bracing panel. The third one is the X bracing panel. So this is the primary member, leg member, and this is a bracing member. Then I will come back to the secondary members later on. So you can see the load subjected. The tower is subjected to 3 types of loads. One is wind load acting on the conductor, and vertical load because of conductor weight, and broken wire loads. Sometimes what will happen when you have a conductor on both sides, suddenly some accident may occur, or conductor may the span between 2 towers may not be equal. That means that will create an unbalanced longitudinal pull. That is called longitudinal load. Based on the voltage classification, we have different types of categories. One is structural configuration, that is self-supporting. It is having vertical or horizontal configuration. Then we have guide mast. Then we have a monopole. Number of circuits it carries, it is a single circuit, double circuit, and multi-circuit. And we have suspension towers. It goes in straight line, that is called suspension towers. Then tension towers. The angle may deviate from the line, it may deviate from 0 to 60 degree. And then we call it a dead end tower, where it ends, the conductor ends, that is called dead end tower. Then special type of structures, river crossing towers. When there is a river, for example, in the Ganga River in Calcutta, we have around 240-meter height transmission line tower, 400 kV, double circuit. There, the single span is 1 kilometer. So we need a very big structure, that is very high, tall structure, that is called river crossing towers. Then it may be crossing a railway or a highway. There we require a very tall structure. So voltage classes, these are the certain voltage classes, 132, varying from 132 to 765. At present in India, we have 765 single circuit, double circuit, 1200 kV trial run. They have erected in near northern region, northern grid. So these are some of the configurations: self-supporting and guide towers. This is a guide tower, portal type, and this is a single mast IVA configuration. And these guide towers, why guide towers is preferred, I will tell you. And if you see the typical transmission line system, these are the towers. Whatever is this box is the towers. These are going in straight line. We cannot take a transmission line tower in straight line, straight path, because we'll have so many obstructions. Maybe a forest, maybe a building, maybe a river, or road crossing. Then we may have to deviate from the line, and that is called angle deviated towers. These towers will be subject to more loads. This particular tower will be subject to more load when compared to these straight line towers. It's a typical guide tower, tested, designed and tested in SCRC, a 400 kV single circuit tower. If you see a self-supported tower, it will be occupying in a space of around 15 meter by 15 meter in the ground, whereas this structure is only occupying a small portion, that is called 500 mm by 500 mm, and for guy another 500 mm by 500 mm. And in this structure, all the shear is taken by these guys and compression is taken by this column. If you see, if you apply a load, horizontal load, this guy will come into action, and this will form a triangular, basic triangle, and it will take the load, whereas the backside guy will be slackened. That means zero force. Virtually, you can remove this guy also. To that extent, it will be slackened. So this is a finite element model of the guy tower, and you can see it's a longitudinal load. When that longitudinal load is applied, one guy is slackening. There's a top view, and this has been tested and it has been published in structural stability and dynamics. And poles, this is called monopoles. If you see in an urban area, we don't have sufficient space. Getting land is very, very difficult task. So we have to go for a monopoles, though it is costly, economically more cost, but it occupies a very less space. Since if you see, this is a 400 kV double circuit tower, which is occupying by 15 meter by 15 meter in the ground. When it is a self-supporting structure, when it becomes a pole, it occupies only 1.5 meter diameter. So you can see in the street light itself, we have it is going along the road itself. So this is the advantage of monopole, but weight will be more, and at present it is economically not that much viable compared to self-supporting structures. But if you see in Delhi, where the land costs and other things are very heavy, they are using these monopoles, and in Chennai also some places it is there, and Bangalore also we have in some places. This is a power grid map of India, Power Grid Corporation of India. We have around 4.14 lakh circuit kilometers. We call this circuit kilometers, it is in terms of conductor length, and we have the idea is to give power to nook and corner of the villages. As I said, the conductor, the overall system, if you see a transmission line system, suppose if it costs 100 crores, in that 33 crores goes to conductor, that cannot be reduced. Whereas towers will be taking around 33%, 33 crores. That means here is the chance for optimization. So whatever optimization you can do, you can reduce the cost here only, whereas the foundation we cannot reduce, fittings and insulator, land rentals, these things cannot be decreased. Only in the tower we can do some optimization. How much we can optimize is required, since it is no human occupancy. The basic idea is we can afford to lose some towers instead of putting more weight, more cost on that, because we will lose some power. Power will be not there for about 3-4 days. It can be restored by emergency restoration systems. So in that philosophy, the transmission line systems are designed for the optimum loads, that is maximum loads and ultimate stresses. There is no factor of safety involved in transmission line tower design. The only criteria is whatever design you follow, you are free to follow whatever panel detailing, K bracing, X bracing, any angle section. But only thing, you have to prove your design by prototype testing. You have to full scale prototype testing you have to do. And once the tower passes that test, then only that tower can be installed. This is a system, typical transmission line system, single circuit. You can see conductor. Once the conductor is connected to an insulator, it will take a shape that is called catenary shape. So it is idealized as a parabolic shape for easy calculation. And the top red line is in a earth wire, 2 earth wires running through the system. And we call this is a span, bottommost point from this to this. We call it as a span, weight span. And we call wind span. Wind span is half of this and half of this will govern the wind span. Based on that, loads are calculated in the system. If you see a typical transmission line system, these red lines are wind load acting on the conductor perpendicular to the conductor direction, and these green lines are vertical loads, that is self weight of the conductors. And if you see broken wire, when this system is intact, there is no broken wire except the deviation loads. Once this system, in this system, one of the conductors is broken, then this becomes unbalanced like this. So one side there will be a pull, and this is though it is a dynamic, this is simplified into a static by using a factor of 2 or 2.5, and it is converted into static load, and these loads are applied in the tower and tested in the prototype testing. So these are the three types of loads: wind load on conductor, it's a bare conductor, or an ice covered conductor; wind load on insulated string, and loads due to line deviation, and wind load acting on the tower itself, because tower is obstructing the wind, so loads are created in the tower because of that. So then longitudinal loads due to unequal spans, as I said, and broken conductors and dead ending of towers. Dead ending means one side conductor will not be there, other side conductor will be there. Then vertical loads, weight of bare conductors, or sometimes wherever ice is there, ice including ice, it will increase the weight. Then insulator and hardware. Then when we are doing serviceability, then man with the tools will be going, for even for that we have to check the tower. Some members will be critical in that tower. If you see a typical conductor in ice zone, see, you can see the conductor is surrounded by an ice. Though conductor is generating in a temperature, this much ice is getting created there. So this will increase your weight of the conductor. At the same time, your span sag will reduce because lower temperature. All these things are taken into account, and loads are calculated for all the conditions: maximum temperature and minimum temperature. So this is the typical transmission. Verticals are support structure, that is a tower, and this is a span, weight span and wind span. So now we have been given a tower. How to calculate the height of the tower? It depends on the minimum ground clearance. Suppose voltage, you know the voltage class, we can find out the minimum ground clearance required for electrical clearances. Then at midspan, what is the clearance required from one conductor to other conductor? That will dictate this height, H1, H2. Then H3 is the vertical distance between three conductors. Then H4 is how much height we have to give for peak in order to have a shielding of maximum 30 degree it can shield, so that the conductor passes inside that shielding, so that there is no thunderstorms affecting the conductor. Otherwise, high voltage will enter into the conductor, and every total height is known from these H1 plus H2, H3, H4. Once your height is fixed, then we will be calculating the loads. Based on the Indian electricity rules, we have for 132 kV 6.1 meter ground clearance, 227 meters, and 400 kV 8.84 meters. Based on this, we can calculate the height of the structure. Once you know the height of the structure, once you know the loads, you can find out the base moment. Based on the base moment, we can find out the base width of the tower. This is an empirical formula. So for a new person who is trying to start the design of a transmission tower, these are the thumb rules, or we can see empirical formula can be used to fix the base width. So it is the ratio of base width to total height is 1/5 to 1/10 of the height. Then based on the side fit relationship between base width and the moment, you can find out the base width also. Then we have probable tower weight. How much weight? Suppose we are quoting for the tower, we can find out the weight of the tower also. So what is the best configuration? So for a self-supporting structure, I have three cases. See, this we call this an amper portion, then straight portion. So once you find out the resultant of the loads acting on this tower, if this resultant of the loads are acting below this cone, then it will be more economical and reliable tower. That means both the leg members and bracing members will contribute to the load resistance. Whereas in this case, the apex resultant loads is acting on the apex, only leg members will take the load. The third case, we have the resultant loads acting on the tower above that crest. That means it will create additional moments, and only leg members are loaded. It becomes very uneconomical. The case 2 is more economical. It's a typical transmission tower and the ground clearances. See, suppose if we see here, conductor, it will swing. In the midspan, it will swing, and when it swings, we have different types of vibrations, alien vibrations and other things. I am not going into that. So this conductor will touch, it should not touch to the body of the tower. That is the idea. So the maximum swing angle will be taken from that, clearances will be worked out. A typical insulator string, V string, is shown in the bottom. You can see here. The same string is used here. We have different types of insulators: polymer insulator, glass insulators, and porcelain. Now porcelain is outdated. So coming to the code, IS 802 Part 1 Section 1, it gives you about the wind load provisions for transmission towers. Basically, this is based on the reliability concept. Previously, it was before 1992, it was deterministic approach. We had a factor of safety is 1.5 and 2 for normal condition, 1.5 for broken wire condition. Now it has become a reliability, code has been changed to reliability levels. We have different reliability levels, 1, 2, and 3. We have based on the return periods 50 and 150, 500 years. It is designed for 50 years return period. That means it is economically viable. Even some tower fails, we can replace. The cost involved and the losses are less. So when you go for above 400 kV, that becomes more important. That means 150 years return period. That means that wind may occur in 150 years or once or twice or something like that. Minimum at least one time. So based on the previous wind data, it has been decided on these 50 years, 150 years, and 500 years. Special towers like river crossing towers, that is a unique tower, that is one tower or two towers only. There we cannot take any chance that tower should not fail. So we'll go for a 500 years. That means the 500 years means the maximum wind that might have occurred in the 500 years, that is taken. And for that, the tower is designed. That means loads will be heavier and your tower will be more and more heavier and more reliable. This is a basic wind map of India. We have different parts. Different parts are experiencing different wind speeds. Basically, this is from IS 875. Only the difference between IS 875 and IS 802 loading is the IS 875, we used to take 3 seconds gust, peak gust. Whereas in IS 802, the 3 seconds peak gust is average over a 10-minute speed. That means when you are averaging, your wind speed will come down. That is, a factor is used, 1.375 factor is used to bring down that wind speed. That, suppose if we say a 55 meter wind, that divided by 1.375, that becomes around 35. For that only, the tower is being designed. So how to find out a wind load on a panel that is given by tower, the wind load on a tower that is given by PD CDT A into GT, the design wind pressure. These things elaborately I'm not going because it will take one more lecture for this. And these are the things given in the code book, so you can go through also. Similarly, how to calculate the wind on the conductor. See, conductor is connected. Suppose somebody is connected at 20 meter height, and it will there will be a sag of around 8 to 6 meters. So which height we have to take for calculating the wind pressure? That height as a standard for calculating the wind on the conductor. So these factors are given in the code book. Then similarly, wind on the insulator. When your wind is blowing on the insulator, this insulator is not a solid disk. We have an open space like this. So you take 50% of the covered area. So this is a quad porcelain insulator, and this is a glass insulator, and this is polymer insulators. So finally, we will arrive at the loads like this. We call this a load tree. What is the horizontal load? What is the vertical load? And what is the broken wire load? So based on the tower configuration, based on the tower location, the number of broken wires will be decided. For suspension towers, is only one conductor at a time. Testing is done for one conductor at a time, and the tower is checked for one conductor broken. For 15-degree tower, it is two conductors. Two conductors are one ground wire or one conductor. For dead-end towers, all conductors broken has to be checked because on the other side there will not be any conductor. So coming to the tower analysis, we can do a simple truss analysis. 3D space truss can be used, and this will give 95% accurate results. And we can go for linear static analysis. People are using linear static analysis only. We will get a 90%. Whatever software you use, if you are properly modeling all the members, then we'll get definitely 95% accuracy. The forces will not change. Consider this transmission line towers are considered as basically a system where only loads are tension and compression. The members are subjected to tension and compression only. There is no bending, though small amount of bending will be there. That will be less than 2 to 3% or 4%. bending comes from the rigidity, semi-rigid, we can say, even not even semi-rigid, because it's a bolted connection. Some amount of bending will be there. Then you can use generally 3D truss element, or you can use a 3D beam elements. The main difference is if you take a truss element, we cannot model the secondary members. That means intermediate nodes we cannot give. Once we give an intermediate nodes, there we have to give a, you have to restrain that nodes. Otherwise, it will instability problem will come. That is the problem. If you go for a beam element or beam column element, the difference between beam element and beam column is subject to both axial compression as well as axial force. Compression, the moment and compression, whereas beam element only subject to axial force. And then to be analyzed all critical loads, when you analyze the transmission tower, we will come up with an around 20 to 30 load combinations. That is top conductor broken, middle conductor broken, a normal condition, minimum vertical, maximum vertical. It depends on minimum temperature, maximum temperature. When the temperature is maximum, your sag will be more, your load will be more, all those things will be there. When the temperature is less, your sag will become less and the loads will change. So we have to check for all these combinations, and we cannot say for a particular load case, the member will be critical. For that particular load case, one member may be critical. For other load case, maybe some other member is critical. So we have to analyze all the load cases, and then we have to come up with a table where it shows maximum load and maximum force in the member and minimum force. From that we have to pick up and we have to design the tower based on that. Then 3D beam elements also you can use. See, when you go for a 3D beam element or beam column, the advantage is we can model all the secondary members. Secondary member plays an important role in the stability of the structure, and we can how to model this. Definitely we have to model with secondary members, and we have to go for a non-linear static analysis where your forces will increase for a tall structures, where your base width is very less and height is more, narrow base towers. There it contributes around 10%. Your forces in the members will increase by 10%, whereas in linear static will be showing some forces. There, if you go for non-linear static, the member forces will be much higher than these linear static forces. For guide towers, geometric and material nonlinearity is involved because guide is a nonlinear element, it's a cable element. So we have to definitely go for nonlinear static analysis one. So this is the analysis part. You can use a beam element. Suppose if you want to know the further stresses across the cross section of an angle section, we need to go for a plate element, plate shell elements. We have both plate. I think plate and plate shell elements is known to everybody. So this is a typical model of a transmission tower. This is taken from Nostron. We are using a Nostron modeling, and here we can model all the secondary members. How we get these places, and we can see by doing nonlinear static analysis, we can find out to transmission tower, the communication towers. Coming to communication towers, these are also very similar to transmission towers. Only thing is here the loads and everything is same, except conductor will not be there. Conductor loads will not be there. The tower wind and tower body is same as transmission towers. And this at present the communication towers are designed using IS 802 or IS 800, but this, wind loads are taken from IS 875. And the other procedure is similar to the transmission towers. Only thing here, the maximum load comes from the antenna. 60 to 75% of wind is from tower, and 25 to 35% wind is flowed from antenna. Whatever antenna, any number of antenna you put, the structure will be attracting more wind when compared to antenna. That is 60%, 60 to 70% is contributed from structure. Suppose if you have an 100-meter tower, the loads coming on the structure will be from the structure itself. And we have IS 875 for calculation of wind loads. So these are some of the antennas. Antenna with radome, without radome, that is cover. The antenna with this type of cover will attract less force compared to this type of antenna without cover. That means there will be more wind coming into the antenna because of that cover is tearing up. The typical structure, microwave tower structure, where you can see a lot of cables. This will attract more force, and a ladder and other things. So you can see antenna with radome, circular antenna, parabolic antenna, so many antennas. And this will produce more wind loads on the structure. The typical FE model of a communication tower, triangular communication tower. It's a typical guide tower. See, these guide towers are more advantageous. This will be very less load, very less weight. You can see we have designed this guide tower 30 meters for northeast region where we cannot get a plain ground of very big size. So we can get a less plain ground. There we can use this basic base width of this tower is only 400 mm, 400 mm triangle, and height is around 30 meters. And we have measured all the guide forces using a load cell attached to a control system, real-time digital control system. And you can see all horizontal loads, calculated horizontal loads are applied to the structure, and full-scale testing was done. Now we will see the design part of the transmission line towers, IS 802 2016. So I will talk about basic things. Angle section. If you see an angle section, 100% in transmission towers, angle section, steel angle sections are used. We have 3 grades of steel angle sections. Mild steel. Previously, mild steel were used. Now, high strength steels are used with yield strength of 300, 350, and we have 400 also. 400 is now people are not that much using because it's a super high tensile steel. It is a more brittle, and this elongation is less there. So we cannot use that. Those steel we will be limiting to up to 350 MPa only. And an angle section is open section. The CG, we cannot apply the loads on CG. The loads are applied to these flanges, and it is away from CG, and it creates biaxial moment. And these things are being taken into account in the codal books by reducing the stresses, thereby increasing the allowable standardization ratio. Standardization will be increased, and your stresses will be brought down so that it will be safer. So if you see this angle section, we cannot connect a bolt and a CG because CG distance will be very, very close to this flange. So we may be using a gauge lens. We call this as a gauge lens. It is away from CG. Depending on the leg length, that means suppose if it is an 50-50 by 6 mm, we will have only one gauge line. That is, bolt will be connected by in the one line only. Suppose we have 200 by 20 section, the bolts can be connected in 2 lines. We call it as a 2 gauge line system. We can stagger the bolts in such a way that there will not be any failure of black shear and other failures. As a typical angle section subject to tension, how the failure path will be there. You see this is the critical path. Suppose if you take the first one, top, you have one bolt here, other bolt here. So directly you gross area minus 2 bolts you can detect. Suppose the path is like this, then we have to take the first hole fully, then the next corresponding holes, part of the holes will be contributing in the failure. So that reduced area we have to take. So the area has to be reduced for these bolts also, and it becomes, this is called black shear. This can be avoided by providing the sufficient pitch distance and sufficient gauge distance. See, this is the formula that is being used for the reduction of gross area for bolt in the failure path. So each portion, the first hole will contribute full portion, the next hole will contribute part of that, but maybe around 80 to 90%. When you calculate this, it becomes 80 to 90% like that. 1 minus P square by 4 GD. P is the pitch and G is the gauge distance, and D is the diameter of the bolt. Now I have an angle section. How much it is contributing? See, only I have a bracing member that is flange full area, and this flange you have to take partial portion only because it will not be contributing. This is called a shear lag in IS 800. Here we are reducing this area by giving this formula 3A1 by 3A1 plus A2. A2 is the outstanding flange area. A1 is the connected flange area. So this comes to around 60 to 70% of this area. So this area is taken full and this area is taken, because when you are connecting the angle section near the leg portion or somewhere, this entire cross section will not be contributing for in tension. Only this connected flange will be contributing. Beyond certain length, it will start contributing. That is called shear lag effect. And these things can be avoided by taking this type of area. When you have two angles connected as a T section by one flange only, then we have separate formula, how much the contribution from the other flange, provided that is intermediately connected, that is connecting bolts are there at every half meter or 1 meter. Then coming to the buckling you had a nice session now, and just I will touch up on to. See, I have a typical angle section. What will happen when I'm applying a load about CG? Let us take. I'm applying a load about CG. What will happen? This angle section will try to deform. Either it will go to this direction or this direction. Out of plane buckling. We call this out of plane buckling about Z axis or VV axis. So and X axis are involved. The section cross section is translating in X and Y axis. That creates a minimum axis buckling. And now purposely what I am doing, I want to arrest this translation along XX direction. Now I am putting a member here that is called secondary bracing. I am putting a member. This member is very rigid on its own plane. In this plane, it is very rigid. It cannot elongate or it cannot get compressed unless the force is more. That means it prevents the translation in this direction. But whereas the out of plane direction, that is the Y-way direction, it cannot prevent. It acts as a hinge. So the member can translate in Y direction. That is only in Y direction it can translate. That means from YY, from VV axis buckling, the buckling mode is transferred to major axis, XX axis or YY axis. That means your buckling strength will increase once you put the secondary bracing. That's what is shown here. There is a minimum axis buckling. Then major axis. This becomes major axis buckling. So this is the main purpose of secondary bracing members. How long we can put? How many members we can? Secondary members you can put? We can go on increase L by decrease the L by R so long as that buckling strength is equivalent to Fy yield stress up to yield stress level. That means maybe your L by R will be on the range of 20 to 25 or 30. Beyond that, even if you put the secondary also, there is no use. Up to your maximum stress is yield stress. And some portions, the members are in such a way designed that L by R is very less, 20, where your tension capacity and compression capacity will be almost equal. Because of holes, number of holes in the member, the net section area will be less and the tension member will be governing. So some members will be governed by tension also, not only compression, tension also it is governed. So the all members, since the system is subject to tension and compression system, all members are same member is checked for compression as well as tension. For both the forces, it has been checked. See a typical system. Say I have a bracing. Let us take a bracing. AB is a bracing, K bracing. When there is no secondary bracing, what will happen? I have the now plane area AB. This AB will try to buckle about, deform about towards me or to opposite to me. So that means out of plane buckling. So it will try to come in the out of plane deform. That is called RVB, minor axis buckling. Now I want to prevent that. I am putting a secondary bracing like this. So this secondary bracing, what it will do? Now this will not be allowing. Sorry, I made a mistake. See, AB will be deforming about in this plane, in the same plane, the in plane buckling. When there is no secondary member, it will be deforming about like this or like this. That means in plane buckling. That is RVB. Now, once I put a secondary bracing, it cannot deform in this plane, this same plane. It cannot deform either this way or this way. It has to deform towards me or out of perpendicular to me, in the other direction of me. So it has to deform towards me. That means out of plane buckling. This is called out of plane buckling. That is called major axis buckling. So this, by putting these two secondary bracings, I am changing the buckling mode from minor axis in plane buckling to out of plane buckling. That is the criteria used for design of the transmission line towers. Now, the further I have a chance to increase the effective stress. Still, I am not reaching the yield stress. Still, there is a chance to increase the capacity of the member. What I can do, I can put a hip bracing. See the member connecting a cross member connecting this AB to the other plane main bracing member. This is called hip bracing. This hip bracing, what it will do? It will not allow the member to go in the out of plane. That means your effective length will become AB by 2. So now this member can buckle in the in plane from this portion to this portion. The half length, that means L by 2, 0.5 L RVV. So this is the philosophy used in the angle member design. The provided the bracing, the other plane bracing members should have a tension of 75%. Suppose this bracing member AB is subjected to 10 tons, at least 7 to 6 tons tension load should be there in the other side bracing. Otherwise, that is also subject to the compression, means there is no meaning in putting that hip bracing. That member will pull away, that will come along with this member in the outer plane. And these are the limitations. The leg members are generally designed in the inelastic range of buckling, where the stresses will be, the entire cross section will be reaching the yield stress. That's why that is being limited to 120. Normally, people will be using around maximum 60 to 70. LBR will be 60 to 70. Although port says up to 120, the demands around 60 to 70. That will be more economical. Then for bracing members, port is giving 200, but it is 150. Our experiments and our observations in testing station, it is observed beyond 170, the bracing members will not be effective. So this has been recommended to code. Now they are reduced to 150. And the secondary bracing is designed based on LBR 250, limitations 250, and at the same time that bracing has to be checked for 2.5% of the axial force in the main bracing, which it is supporting. In some cases, it crosses 2.5% also. It comes to 3 to 4% also. Normally, the people, mostly the secondary bracings are not modeled in the analysis, and they are designed by using 250 LBR's limitations. At the same time, the main bracing member or main leg members, which these secondary bracings are supporting, this will have, the secondary bracing should have a sufficient stiffness of the main bracing members, else it will not be useful. The maximum permissible value of B by T is around 25. Beyond 25, you should not use. And as the yield stress increases, member yield stress, suppose we are going for mild steel to high strength 350, the same member 1990, suppose if I am taking a 1990 by 6 angle section, which is not falling in the local buckling, that is plate buckling mode, may fall in plate buckling mode when I am going for yield stress 350. So because as the yield stress increases, the plate buckling chances also more. We have to check for that also. So what is the effect of secondary bracings on a panel? Let us see an X-braced panel. This leg member is divided into two parts. This plane and the other plane, both the planes, it is divided into two portions. Then your weight will be around 3.6 tons. Suppose I have a secondary bracing. I am in plane buckling, I am preventing by putting a secondary bracing. And in that case, it becomes 2860. Total weight of the panel becomes 2860. And when I am putting a hip bracing also, and there is a tension compression system, this bracing is subjected to, this bracing is subject to compression tension. Similarly, the other plane bracing also subject to tension compression, then it comes to 2.6. So this is the idea how the secondary bracing helps you in reducing the buckling length, effective standardization ratio, in reducing the standardization ratio and increase the buckling capacity, compression capacity of the member. So we have around 27% advantage when compared to case 1. So how to use the secondary bracing? See, this is a system where we have an isolated hip bracing used, and there is no triangulation in that from other side of the, if you see from that corner, there is no triangulation. So this should not be used like this. You should be used the yellow magenta color. You have to fully triangulate the hip bracings also, not only this elevation, the hip side also you have to fully triangulate. The typical panel, 3 panels. See how secondary bracings can be used. See, this is not allowed where there is no triangulation. You can see here, this will give a instability problem, these two. Whereas here, if it is in the top right corner, this fully triangulated hip bracing. This will be more effective provided one member is in compression, other member is in tension. And we have a compression member design, effective length factors. These similar to IS 800, here also effective length factors based on the end conditions and based on the standardization ratio. Suppose I have a leg member which is connected, the leg member is connected on both the flanges. The angles, the bracings are connected, and both the flanges are subjected to is equal to KL by R. K is 1. And the third one, if you come to a member with eccentric loading at one end and normal framing eccentricity at the other end, that means the one side it is a concentric load, other side is an eccentric. This cannot be avoided. How I will show you. So in that type of case, I am penalizing the member by reducing the stresses. That means I am increasing, purposely I am increasing the length of the slenderness ratio of the member. Suppose my actual slenderness ratio is 100. If you put it in the formula, 30 plus 100, 0.7500 means 75 plus 30, around 105. Instead of 100, I am taking 105. That means I have an eccentricity at one end only. So I am increasing the slenderness ratio and decreasing the stresses in order to account for this eccentricity. Now I have a member, it is having both sides eccentricity, top also eccentricity and bottom also eccentricity. In that case, I am much more penalizing that member. I am reducing my stresses by putting 60 plus 0.5 L by R. That is 0.5 into 100, that becomes 50 and this 60. So 110. Instead of 100, I am taking 110 L by R. That means our stresses is reducing due to this eccentricity on both ends. I am accounting this eccentricity by reducing my stresses by then a member partially restrained. Suppose beyond 120, that is up to 120, we are assuming it as a elastic limit. Beyond 120, it is elastic limit. Below that, it is inelastic limit. And this is decided by, you see, 0.5 Fi. Up to 0.5 Fi, beyond 0.5 Fi, it is assumed as elastic members. Below 0.5 Fi, it is assumed as inelastic members. So based on that, suppose if your LBR is 120, more than 120, what will happen? If more than 120, eccentricity will not have that much effect because already your member is having very slender. By self-weight itself, it starts deforming in the perpendicular to the plane of the loading. So in that type of case, the restraint, end restraint will give you advantage. Suppose partially restrained against rotation at one end of the unsupported. Suppose I have two bolts on one end and one bolt only on the other end. That means hinge at the one end. On the top, it is a partially restrained. In that case, you can take 28.6 plus 0.762. That means L by R will be 120, 130. Let us take 130. That will reduce to 125. That means I can use that additional stresses because of end restraint at the one corner. Similarly, when I have both sides restrained, that means I have two bolts on both sides. That means your effective length will reduce further. That is buckling length will reduce. So there you can have more capacity. That is 46.2 plus 0.615. This I will show you in the curve forms. That will be better understanding. For better understanding, that will be useful. So these are the actual compression capacity of a member. How to calculate the member capacity using this formula. Beyond 120, beyond 120, you can use directly pi square EA by L square. Below 120, these are the stresses. To find out the stresses, this is a CC limit. CC limit is called as an elastic buckling limit, critical point. This is given by pi into 2E by Fi. This is derived based on assuming 0.5 Fi. Based on that, it has been derived. And B by T limit. See, given a section, you have to find out B by T limit. This is the limit up to which there is no local plate buckling stresses will be coming. Your angle will behave as a angle section. Beyond, if it crosses this, your angle may be subjected to individual plate behavior, and plate buckling will be dominant when compared to the overall buckling. Before overall buckling occurs, your angle will fail by plate buckling. Say suppose CC limit, if you see the CC limit, for mild steel it is 124, for 300 MPa steel it is 114, it will reduce because 210 by root Fi, CC limit will reduce, and for 350 MPa it is 106. And even if you go for highest strength, it will become less. So below this, it is called as inelastic, and after that, it is elastic column. And suppose B by T limit is 210 by root Fi. Suppose I am taking an 100 by 6 or 110 by 6 mm. What will happen? Your section will be subjected to B by T. Suppose for mild steel, it is 13.15. For Fi, as Fi increases, your B by T limit decreases. The same member which is not falling in B by T limit in mild steel, it may fall in B by T limit in high strength steel. So that number has to be checked for that plate buckling stresses also. And then the next limit is B by T calculated is less than B by T limit. Use Fi. Fi is same Fi you can use. No need to reduce the allowable stresses, directly you can use. Suppose your Fi is crossing beyond that limit, then you have to reduce your Fi. Instead of Fi, use FCR in the first formula. That means my Fi itself I am reducing in order to account for local plate buckling effects. So Beyond that, even further, if it is not satisfying, then it is going maximum. It is 23.67. Then we have to use this formula. FCR is 65,550 into B by T square. So B by T only will governs. That is plate buckling only governs. So FCR critical stress, we have to use this one only. If you see this curve, you can see inelastic buckling and elastic buckling. The elastic buckling range is pi square EA by L square. For mild steel, it is around 120. And this is the inelastic range. As I told you, it is derived from 0.5 Fi, P critical. That formula is coming from here, 0.5 Fi. Based on that, that CC limit is coming. You can see here, P critical by area is equal to Fi by 2. From that, it is coming, CC limit is coming. The member will fail. Let us see. See, this is the member, typical leg member. Both sides we have secondary bracing, both sides connected. See, if you see this yellow color drawing, if you see, this is the effective length of the leg member. That means this member can deform in the in plane in this direction, in this length only, in this particular length. That means total length divided by 3, one third length. And this may deform this way. So each portion becomes effective length. So L is the measured length. So L by R, K factor is only 1 here. K L by R is equal to L by R. Now the similar things, suppose I have a secondary bracing in only one plane, what will happen? Let us see. See, this is the member, leg member. I have secondary in only one plane. In the other plane, it is not there. Then what will happen? It will come out of plane buckling will occur. See, if you see in the yellow drawing, you can see this is the effective length. This member will be coming in the out of plane. So we have to take this much length we have to take for effective length. So you can see the difference between that in plane buckling, or minimum axis buckling and major axis buckling in a leg member, typical leg member. Now coming to the bracing, I have 2 bolts here, the bottom, I have 1 bolt there. What will happen? My L by R is 100. I have an eccentricity here. One side eccentricity, other side there is no eccentricity, because this member is eccentrically connected here because of other bracing is coming here in the same plane. So my L by R is increasing by 105 because eccentricity on one plane. Suppose I have a K bracing, there is an eccentricity, this belt member is there, this bracing member is connected over that gasket plate. That means there I have an eccentricity. Similarly, here also one gasket plate will be there. This member is connected over that gasket plate. That means eccentricity on both sides we have. Then we have to use the 60 plus 0.5 L by R. That means the original L by R is 100. Now the actual L by R, the modified L by R will become 110. That means I am reducing my stresses, allowable stresses, thereby my capacity in order to account for the eccentricity on both the ends. Now coming to the, suppose my member is more than L by R 120, that is failing by in the elastic range, where eccentricity will not matter, only end restraint will matter, because already this member is very slender by its own self. Once you start deforming, it will get deformed. See, I have 2 bolts here, I have only 1 bolt here. That means this end is partially restrained. That means partially restrained. That means your effective length will start from here. The bending will start from somewhere after certain distance, and it continues up to this intersection point. Assuming that the other member is having fully tension, equivalent to 75% of tension, it is equivalent to that. Suppose it is 10 tons, that 7.5 tons tension is there. One is subject to tension, other is subject to compression. Then it's partially restrained at one end. L by R is 120, beyond 120. Then your, suppose if I take L by R 150, your K L by R will become 142.9. So that means I am reducing my actual L by R by 8. That means I am increasing the stresses. The capacity is increasing. The second case, if you see, I have 2 bolts on both the sides, and our L by R is in the elastic range. And you can see see here, the buckling starts after certain distance. This is your effective length will reduce drastically. That if you see here, same L by R 150, so K L by R will become 138.45. That means I have restraint on both the ends. So I am using this advantage. All these curves are fixed based on the experimental values. Our Indian 802 is based on ASC 1015. So all these things are based on experimental. So all these factors are based on experimental values. Now you can see whatever formula is shown, the curve in the form of curve. You can see the original IS 802 was having these curves. Now all has become formulas. You can see the yellow line, curve 1, KL by is equal to L by R, both sides concentric. That is, it is the topmost portion. That is a maximum capacity. The next one is, I have an eccentricity on one end. Your allowable stresses are reducing. The third one is curve 3. I have eccentricity on both sides. That means your allowable stresses are drastically reducing. Once you cross 120, the elastic range, this curve is increasing. That means I have partial restraint on both the sides. That means your allowable stresses are much more higher when compared to a member that is having partial restraint on only one end. Then the third one is yellow color. That is, I don't have any partial restraint on any single bolt on both sides. That means it is acting as a hinge. Then there is a least capacity. Is having the least capacity. So why IS 800 is not being used? Only 802. This is an industry-driven code. IS 802. The IS we have tried to have a unified code of IS 800 instead of IS 802, because all steel structures are governed by IS 800. This industry is arguing that since we are going for testing, we don't want to go for IS 800. If you see from this itself, we can conclude that IS 800 curve B for angle sections is having lower allowable stresses when compared to IS 802. And this is BSN is Euro code, you can say, or BS now. There is intermediary. So this industry is much more dominating BAS, and they are not allowing to change it to IS 802 to IS 800. Now it has been finally settled to IS 802 only. And this is the similar curve with partial safety factor on IS 800, without partial safety factor. With partial safety factor, curve B. See, this is the difference. That's why industry is not coming to IS 800. For different sections, 100 by 6, 100 by 8, what will happen? For IS 802 and IS 800 and BS codes. BS code is a blue color, that is intermediate, and black color. This is so much difference is there. That's why people are, in the elastic range, all are same only. In the inelastic range, mostly these members are falling below 120 in the tower. So it is not being allowed. They are using IS 802 only. If you see the non-dimensional curve, you can see around 70% difference. 70%. This is one. If you take it as a 1, IS 802, there's a 30% gap. I'm requesting to bear for few minutes to load the other lecture. Is it visible now? Dear Vignesh?
No, sir. Actually, it's not visible, sir.
Not visible. Now I am starting failure analysis. Just
Okay, sir.
okay.
I think in bottom of the screen there will be a share screen option, or it will be in the right top, sir.
Right up.
Right top, it might be there.
Right up, it is there. Start getting. Okay, now we'll see. Though the towers are designed based on IS, as I said, for some of the failures, I use around 7 to 8% failures are encountered in testing, And if you see in that, maximum is because of secondary bracings, or because of bolt quality, or because of material quality, and assumptions, some assumptions. In this study, I used Nastran, a finite element software, for modeling the members. I have modeled some of the members. I have modeled as a beam column. Some of them as plate shell elements, where you can have in plane and out of plane, and plate elements, in order to find out the stresses across the member, cross section, that is angle section, cross section. If we want to find out the stresses across the member, distribution of stresses, then we have to go for a plate element to understand that one. If you go for a line element, that is a beam column element, though this program is having a shape, you can give any shape, L section, I section, other channel section, other things. The limit load will be reaching when the stresses and the defined points reaches the yield stress, and the structure reaches the instability. We cannot find out the stresses across. So material model is elastoplastic bilinear model with modulus of elasticity, and post-yield stiffness identified as tangent modulus. I have approximated the stress strain curve as beyond yielding, it is a 2000 MPa modulus, and 2e power 5 below yielding. Incremental load and a predictor characterization is used, modified Newton Raphson method, isotropic ordering, all these things we may be knowing. I will go to the topic. So a typical transmission line tower is a 760 kV double circuit tower. This structure is a reputed concern only, reputed designers only. The most of the structures fails by detailing. Detailing plays a very important role in transmission towers, because we have so many members, we have so many joints, we have different types of, we have all types of joints, lap joint, butt joint, single cover butt joint, double cover butt joint. So many joints are there, and different grades of bolts. We have 5.6, 8.8, 10.8, different grades of bolts and different diameters of bolts. And sometimes fabrication error also. Suppose instead of, I have a 16 dia bolt, instead of drilling a 17.5 hole, if I am drilling an 18.5 hole, and there is a mismatch of holes also, then a group of bolts, in the system of group of bolts, one bolt, the first bolt which is having a bearing with the member, will fail first. So that will cause the failure, trigger the failure in that joint. Because of what? That particular joint, the tower may get collapsed. So now in this case, the 765 case, I'm going to show you the failure. These are loads applied on this. Are 76 kilonewtons, and these are the conductors. And here, if you see the particular tower, the failure has occurred. If you see the second drawing, the second middle figure, the peak, ground wire peak. If you see this bottom, this back member, it's coming and meeting with the cross arm member. This is the cross arm, and this is a slanting member. This is acting as a continuity of that peak, ground wire peak leg member. If you see here, the failure has, for the first time, the failure has occurred here, like this local plate buckling, like similar to this, and this has steered. This has happened because you see here, this is the member that coming from ground wire. You can see here, red line, red arrow. This is the member that is connected to the cross arm with a gusset, and from there it is connected to the leg member. Instead of connecting to the leg member, this has been connected to the cross arm member. If you see here, elevation drawing, you can see this member number 587. The 601H is connected to 587 directly, not to the leg member, not to this gusset plate. So what is happening? Any analysis, whoever is doing whatever software we are using a line model. We are assuming that all members are getting connected in the CG lines. That is the problem, and we are not going for this detailing, the inner detailing. We are not modeling the eccentricity. We are not modeling the bolts. We are not modeling the connection. So whatever we are doing is we are making a 3D truss analysis or 3D beam element design. So the first time it has failed. Then second time on, we have noticed that even by putting the cross bolts, additional bolts, it was deforming like this. Then only it has been realized. We have analyzed this. There is a gap of around 100 mm, 100 to 75 to 100 mm between leg member and this peak member connecting to the cross arm members. So if you see the member force in the cross arm 587H, In this particular small region, it is increasing by about 10%. That 10% force is causing the failure, additional force. Because of this member is getting connected here, it is causing the failure of the cross arm member. Otherwise, the cross arm is having good factor of safety, but still it has failed because of this member is being connected to the cross arm member. Then finally, what they did, if you see here, the bottom left corner, we have two different figures. 587, 601 connecting to the 601 connecting to 587, whereas in the other figure, 601 connecting to a extended gusset plate. See, after connecting to this extended gusset plate, this tower has passed and there is no failure noticed in the main cross arm member. So unless you do, it's a post-mortem only, you will not be knowing when you are designing, because we will be finally coming up with a line sketch. This line sketch will be given to the detailer and number of bolts will be specified, force will be specified. The detailer, suppose if he is having good knowledge of detailing, then we will be detailing it properly. Otherwise, this type of small mistakes will occur. That will cost you very much. This is a detailing, typical detailing failure, we can say. Next, I will show the structural failure. It's a same tower. That case, it has overcome that case after changing the gusset plate and changing the peak member, connecting to the leg member through gusset plate. The next case, when we are doing a broken wire condition of top conductor broken and ground wire broken. So the cross arm, you see, it's a T section. We can say T section, two members connected back to back. T section, it has buckled in the off length. You can see the secondary member buckled in the outer plane and this main member has buckled like this. It has happened in two successive panels. Here the problem is when you are going for we call this as a compound member. It's a combination of two members connected together with a stitch bolts at intermediate points with the battens or a plate connected to a bolts. Here is a stitch plate connected with a bolt at every distance of A. A is equivalent to the given conditions are given. It depends on the LVR of individual member, LVR of the overall member. So the transmission towers are fully bolted connections. So I have shown here welded connection. There's not there. Only bolted connections are used. Here in IS 802 or AAC 1015, the compound members are subjected to shear deformation. As you design in the IS 800 batten columns and laced columns, there will be shear deformation will be there because of shear in these battens. This shear deformation, in order to account for the shear deformation, your effective standard ratio has to be reduced. In the BS code, if you see BS or Euro code, there is a reduction in the standard ratio in order to account for the shear deformation. See, this is given by lambda square is equal to lambda naught square plus lambda 1 square, taking a maximum value of this lambda 1 should be 0.75 lambda naught. And this will reduce your LVR and thereby it will reduce your capacity, thereby it will be more safer. When you calculate your capacity based on IS 802, that I am showing here, force in the main bracing member is 464 kilonewton because of that loading, and capacity as per IS 802 or ACE, L by R is equal to KL by R is a 51. After modifying, it is 51.52, and its capacity is 527.7 kilonewton. That is 13.7% margin is there, factor of safety is there. But still, this member has failed. It is the same member if you work out the capacity based on BS capacity with the change modified L by R ratio, capacity is coming to only 457. That means it is lesser than the force in the member. Because of this shear deformation, which is not accounted in our code, this has been recommended to code and is being introduced in the draft now. Because of the shear deformation accountability, this main member has failed. Now coming to the other structure, which is recently tested, 2 times it has failed. There is a limitation, how much length we can have a panel, height, what is the height of the panel that we can have. See, if you see here, the left side, you have a 15-meter panel. There is a body extension, there is a leg extension, 12-meter leg extension, we call this a leg extension, and this is a body 3-meter. 15 meter, for about 12 meters, there is a long panel. 15 meters, if you see this cone, it's a cone, you can say, 2 bracing member, 1 leg member is forming a cone. This cone 180 by 16 section, and bracing member is 100 by 8 mm, and your secondary members are 45 by 5 and 50 by 4. If you see particularly the designation I given B, secondary bracing B and D, 55 by 4 and 50 by 4. This is not having stiffness compared to this 180 by 16, sufficient stiffness, and it is not taking the 2.5%, it is less than 2.5%, and they have fixed this based on LVR limitation 250, and this member has failed like this. See, this cone has failed like this. You can see the typical secondary bracing failure in the second figure, where the secondary bracing is subjected to more than 2.5% and nearing to 250. So LVR 250 limitation alone will not work. You have to check that bracings for the force in that member and axial stiffness of the main member. Then this B member, secondary member B and D was changed later on. The next case it has passed. This another tower in the same line. This tower is meant for Himachal Pradesh, where in hilly terrain we will not get a plain ground. That's why maximum leg extension 15 meters. Within this span of 13 meters, 13 meters the base width. Within that 13 meters, to cast the foundation, one will be the elevation, the heel top, other one will be down. That means the difference in elevation will be more. So instead of, for that purpose, they have maximum deviation, maximum leg extension. That means 12 meters plus 3 meter body extension. That means one leg will be sitting at lower level, other leg will not have 12 meters, it will have only 9 meters. About 3 meters difference in ground level is there. This one leg will have 12 meter extension, other leg will have 9 meters. So, but testing will be doing with the maximum leg extension in order to have a maximum effect. See, this is a dead end tower. This tower has failed twice because of the secondary bracing, and overall cone, if you see the cone, the right side, the cone is not having moment of inertia. Even if you calculate the moment of inertia, as you go down, the moment of inertia is going on reducing, and though it's a truss, space truss, and it is assumed as a tension compression system, the overall stiffness of the structure is very, very less when if you compare this as a column with less column with these members, it is having a less capacity compared to the force coming into the structure. So the 2 times it has failed. Now the 3rd time they are trying to address this by changing this main bracing member into a back-to-back member. We are suggested to reduce the extension, go for a two panel extension. That is, one is 5 meter, 6 meter, another 6 meter, 2K bracings, and they don't want to change the design because already the work has been the foundation and other things are. The capacity it is failing because of instability in the structure, because of this very, very long slender column. Now, if it's coming to this other structure, it's a 400 kV double circuit structure. Suppose you and me, as a new designer, entering into the field, and if you are using the codal provisions and designing a structure, and I am providing a secondary member, and it is failing, what will you do? See, how to interpret the code. Code is a guide only. We have to interpret the code. How it will? We have to think in such a way how to interpret the code. See, here if you see the left side, we have a leg member. The bottommost, if you see, each 4 meter, 3 meter, 3 meter. The bottom 4 meter panel is divided into 2, and elevation we have a triangle form of secondary bracing, and this leg is divided into 2, and bracing is divided into 2. And this portion has failed. I'll show you. See, this is the failure occurred in the successive 2 failures. This is a 3 meter height panel. This is a 4 meter height panel. If you see in the hip raising, the other plane, this is the pattern used. Whereas in the elevation, the only triangle is there. Leg is divided into 2, and the bracing also divided into 2. Whereas in the hip bracing side, we have divided into 4 parts. That means the designer is trying to restrain the bracing member in plane deformation by putting a member in the other plane. See, this bracing, if you see here, this secondary bracing will not, it cannot prevent in plane buckling, because it will come, because it is in the other plane, it will come along with the member down. So that's why it has failed. If you see here, finite element simulation, including the bolted connection. We have modeled the bolted connection using another beam element, which is having a suppose single bolt means rotational stiffness 0. It is a multiple bolts, rotational stiffness proportional to that we have taken. We have simulated that, and we have analyzed that. If you see here, the typical joint near bolted connection, it will be like this. All secondary members connected by bolts with a bolt property. You can see the failure of the member, the magenta color. The compression bracing, it has failed in the successive two panels. The final version I will show. This is so when you want to restrain the member, bracing member or leg member, we cannot restrain that in plane deformations within a out of plane bracing. We have to put a bracing here, the in plane only. That means the elevation only can prevent the in plane deformations. The final version is this one. The right bottom corner, we have you can see the red members. Though leg is divided into 2 only, bracing is a problem. Bracing is divided now into 4 panels, 1, 2, 4 subdivisions. In the elevation as well as in the hip direction. If you see the view A, here A is given, the bracing is divided into 4 sub panels, and the elevation also 4 sub panels. Finally, this tower has passed. So the advice is not to go for a secondary bracing pattern in such a way, assuming that will provide the restraint for the out of plane buckling, in plane buckling. For in plane buckling, only elevation bracing can prevent. According to the designer, we have much capacity and other things. Still, it has failed because of this wrong assumption. See, similar structure is a 400 kV. Here also the same pattern. Elevation. See this length. If we see the right side, this is the circled one, red circled one. If you see this bracing is divided 1, 2, 3. After that, there is no division in the elevation. Whereas in the hip bracing, if you see, there is a division. Here we have some small secondary bracing is there. That is dividing. That is assumed to provide the restraint to the in plane deformation. Whereas actually that has not provided. It cannot provide. So it has buckled like this. You can see here. The best way is to provide a secondary bracing in the elevation also. So this is the failure because of that wrong assumption. And you can see that red arrow, this is the portion, assuming that this portion will buckle in major axis. So this is the finite element model simulation. You can see here the same type of failure. Our finite element will predict, it's a rigid model because we are not modeling every joint, we are not modeling bolted connection. So that will assume a rigid model only. And this has given a failure of 1 or 2%, 2% higher than the test value. The final version is this one, dotted line. The secondary bracing, the elevation has been introduced. After that, this tower has passed. See another bracing failure similar to that one. So you can see here how it fails. The same, you can see the hip bracing and elevation pattern here in the bottom right corner. Same type of failure. Okay, this is the 220 kV tower, dead end tower. It's a typical failure, how it will fail. See here, the problem is bracing is having sufficient strength according to the designer, according to code. The problem is here, hip bracing has been provided as an isolated hip bracing, 2 bracings at 2 places, at top corner and bottom corner. And there is no triangulation in the hip bracing. Because of that, this has failed. This failure has occurred because of that. And this has been simulated in a model with a line element as well as plate element. We just wanted to know the stresses across the member. So it has been modeled with plate element also. This is a line element. Actually, what has happened is this is a hip bracing. You can see here that hip bracing is supposed to be connected in this corner. All the members should join in one place. Whereas for the convenience to avoid a small gusset plate, that hip bracing has been connected away from the leg bracing joint. So that means hip bracing is connected to secondary. So that has not given the assumed restraint and it has failed. And moreover, this is open space. There is no triangulation. This is a typical failure obtained in a plate element model. So now coming to the drawback in the code, see when we have observed in the some of the towers, when the member bracing member L by R is less than 120, it is subject to conservative. They are unconservative because it is not safe. It overestimates the capacity. You see here the system here, the bottom right corner, the bracing compression member has failed. Then the tension member has come to rescue, and the entire force has gone to tension member, and all the bolts got sheared off the tension member. The entire structure has moved as a rigid body, like you can see, the rigid body motion like that. See, bracing capacity 100/7, bracing KLBR is 99, IS 802 capacity is 276, whereas the BS capacity is 260. BS, to some extent, BS estimates to realistic value when compared to bracing members. Leg member is having a very sufficient strength, 923 and 808. So the failure is not because of leg member, failure is because of compression bracing member. Once the compression bracing member has failed, the tension member has given away. All the bolts got sheared off. Similar failure is a special tower. We can say it is having cross arms in 3 directions. That is isolate. This is a dead end tower where isolated structure is kept. Isolator is kept in the top of the tower itself. When you are terminating the conductor will come to the portal structure in the bottom around 10-meter height. There we will have an isolator structure. The conductor is connected to isolator, and from there it is connected to the transformer, other things. So here they wanted to have the isolator also in the tower itself. That's why we have 3-direction cross arm. The perpendicular direction also we have one cross arm. So from conductor will come to this isolator structure, isolator device, and from there it comes as a cable to the substation. So here you can see a failure of the bracing member. There is also inelastic range of buckling. The deficiency in the KL/R factors. The capacity is overestimated by IS 802, 293, and BS is 267. Force is 287. It's another bracing failure, a typical out of plane buckling. When you have this is insufficient secondary bracing. Bracing member force is secondary bracing member force is more than 2.5. Because of that, this bracing, the failure is expected failure only. It has to fail in x only, but because of the secondary, it has happened. So this is a simulation. FE model failure is 105. Test is around 100%. You can see the line model is also giving the same element, same failure. And this is the detailing, another detailing failure I will tell you. If you see, is a 220 kV double circuit dead end tower. See, because of secondary bracing. See, if you see here secondary bracing, this IR and HR, these are having lesser capacity when compared to the leg member. Leg member is 250. And one more detailing failure is here the bracing member, though is a gusset plate is there, he has provided only 1 bolt. And in the leg member connection is with 2 bolts. That means the bearing stress in this bolt near this bolt plate has exceeded and is got teared up. And same time the secondary bracing capacity also less. You can see the buckling of the secondary bracing. And here you have used the plate elements for the leg member and secondary member also plate elements. So how the plate elements, how the bracing member is failing, secondary bracing member. Because of small member, the failure has occurred. So the entire structure has to be removed, and again it has to be erected and tested. It costs more. See, as I said, the capacity of the secondary bracing with IR is a Mach number, 1.37% of leg member force, whereas FEA is attracting around 2.2%. So he has designed that member based on 250 LVR limitation. And instability. When you have a very long structure, it's 75 meters height, and this B by H ratio is very small. That is width is very small, narrow base tower, and we have an extension, large extension. This instability problem comes into the structure, and the tower will fail. If you see here, FE model prediction is around FE model prediction deflection and tower failure prediction, tower at the time of failure deflection is almost same. That means it shows that structure has reached the instability region and it has failed. Members wise, if you see the capacity and everything is same, having very good margins. And some, this is also another detailing failure. This extension, leg extension, the gusset plate is used. This gusset plate will be very strong in its own plane, but it cannot take out of plane buckling. When it starts deforming the out of plane, the entire bracing has to fail. This is a bracing member subjected to compression. Both, suppose all the design is based on the member in a system, X bracing system or K bracing system, is subject, one member is subject to compression, other member is subject to tension. Suppose if both the members are subjected to compression, then we have to take total length of the member into consideration for minimum axis buckling. Else it will buckle, it will come in the out of plane, as both members will come in the out of plane, since both members are subject to compression. And because of that, the tower will collapse like this. And this is again secondary bracing member failure. Because of secondary bracing, it has failed. This is here you can see the secondaries are designed based on 250 LBR limitation. And if time is there, I will show some more. Otherwise, I will close with this. Dear Vignesh.
Yes, sir. Actually, the thing is that the session has exceeded some time limit.
Yes.
Yes, sir. Yes, sir. Sorry, sir. Actually, we couldn't.
Hello.
Sorry, sir. Actually, we couldn't also intimate you in prayer.
Then we will try to close this.
Yes.
Just one slide. I think I will show compare. This is another leg member cross section. How it is failing. You can see local plate buckling type of failure, because stresses in that flange has exceeded. That's why that portion has failed like a plate buckling. The test also it has failed like that. You can see here. See how suppose two members are subject to compression, how it will fail. It is the example. And this detailing failure, one more detailing failure I will show you. With that I will close. See here, hip bracing without triangulation. What will happen? The entire bracing will come out like this. The instability problem will come. Since the entire bracing is coming out of plane, the structure has to collapse and there is no other go. So this is the comparison, final comparison. See leg members. If you see leg members, ASC and IS code are very closer to the capacity. If you go to the bracing member, BS predicts are very good compared to IS and ASC. Okay, with that I will close. So if you want to ask something, you can ask.
Yes, thank you, sir. Thank you very much. And throughout this lecture, we could narrow down that most of the researchers have been having a correlation between compression member capacity design with L/R ratio and reduction of weight of the members. Am I right, sir?
And I didn't hear you properly. Please ask me again.
Yeah, no. Thing is that the entire webinar session and your research work in the TTRS been confined or narrowed down to the 3 parameter correlation, like compression member design with
tension member
with L/R and
yes,
reduction of weight of the members.
How to interpret the code?
Yes, sir. And the interpretation with respect to codes like 800 and 802. Yes, sir. And thank you for the valuable session, sir.
Okay.
On behalf of the department,
I have to thank you and your HOD and your head of the institution for giving me this wonderful opportunity.
Yes, sir.
Yes.
Sorry, sir. Actually, sorry for interrupting. Sir, we like to know what are the possibilities for our students,
yes, sir.
BTech and MTech students, to enroll in TTRS as a project intern.
Yes. I will tell you. See, we have in SCRC, we have skill development programs. There you can UG students also can join, PG students and research scholars also can join, and we have as a job you can join as a junior research fellow or senior research fellow. or a project assistant if you have completed the degree or PG, or as a student you can do BE project, MTech project or ME project, and PhD project also you can. There is an opportunity, and now as it is now, I think it is coming to close. I think it has this year it has closed. Next year you can apply. Your students can apply. They can do project work here. Already we are doing. Many people are doing a PhD. We have a main lab in Taramani, SCRC, Structural Engineering Research Center. There we have more disciplines like earthquake engineering, concrete and composite laboratory, and we can have a fatigue laboratory. We can have a wind engineering, computational dynamics. We have different categories there, different systems. You can work in any whatever field you are interested. You can work. You can work in wind engineering. You can work in seismic laboratory. You can work in steel lab, separate steel lab we are having. We can work in concrete and composite lab. So we have different characters. You can join anywhere. Your students can join.
Sure, sir. Sure, sir. Thank you, sir. Thank you very much for your
Okay.
valuable session.
Okay. Thank you for giving me this opportunity. I once again thank all the students who have listened to this. And I think if I have given something, it's okay. I am happy.
Thank you. Thank you very much, sir.
Okay.
Sure.